Okay, everyone, welcome to DIGA630. We're in week one. We're about to embark upon our spatial analysis workshop. This is really fundamental content that we're going through. And in order to access the necessary material for our term here that we are in, inside of the week one module, there's a folder called, or not a folder, rather a file called Week One Spatial Analysis Manual. So if you'd like to download that, again, you might have to shift or rotate the orientation of that manual. Otherwise, I will be going through that manual with my document camera that I have here in front of the classroom. So we have people in class and we have people joining real-time remote. And then this will be also for those folks who want to watch the grid at a later time, asynchronously, and or people who want to go back and maybe pick up a process. So I'm fully aware that when I'm going to be demonstrating certain things out of this workshop, that all of you are going to have to watch me and minimize your screen and try to replicate what I'm doing. So I understand that, so I'll try not to go too fast, but if I am, just have to tell me to slow up a little bit. And if something crazy happens, what we can do is you can watch me, just follow along. This is all recorded. So you can go back and pick up those steps at any time. And if there's something you want to meet about, after the fact, let me know and we can set up a session and go through some questions. So to that end, I can assure you that there are usually many ways to do things with this content. And this content, we used to have an entire course just on spatial modeling. So we're giving you a few periods on it, but I'm going to step you through kind of going back to just the ground root fundamentals so that we have a really good appreciation, a really good knowledge base of what are some key tips and tricks and good general practices, I guess, that we all might want to be aware of when we're working with general data, raster data, things like that. So in our week one, before we get going too far, there is a course syllabus in there, or a course outline for the period. But in short, you could take a look at that. It's our week one agenda. But in the agenda, that essentially outlines our spatial analysis workshop. And at the conclusion of the workshop, then I'll pause this recording, then I'll make a short overview of the assignment to kind of template that out to help you. But keep in mind that there's going to be a few little nuggets of information, a few little keys that we'll be going through that'll help you in the assignment for next week that we'll be going through in our workshop. And so we'll try to point those out to you, but a lot of just thinking going on. So this will be fun for us for the next few hours here together. So more on the agenda later. So if everyone could please download that spatial analysis manual, that was the first thing. The other thing that folks may want to go into is the spatial workshop and assignment data. And you'll notice that there's a little overview on the assignment data folder there. It's called Grid Training. So if everyone could please go into that portion of your module and just click the arrow down, the down arrow next to the Grid Training folder, and this will be a zip folder. So download that, and that might go to your downloads. And if that does go into your downloads, like it did probably for me here, what I'd like to have folks do is to right click on that zip file, or if you're ahead of me already, that's fine. And you'll want to say extract all. We're going to extract those files out. Now you can either extract those to your downloads, or you can browse to another location. And in this case, that might be the C drive. You might have a DIGA630 folder that you want to create, and that might be a good place to keep your working data for these workshops. So I'd encourage you to pause the recording for folks at home watching this, and maybe set up a folder in your C drive or something called DIGA630, where you could create a folder. Like for me, I created one here called W1 _ 2001. That's just a folder I'm going to work with for our class exercises. You may want to do something similarly, but wherever it is that you are going, to save your data to. I highly recommend, and I'm going to just highlight this out here in the Canvas exercise or in the Canvas module, save that in a working directory with no spaces. Later on today, we're going to talk a lot about rules. What are good practitioner rules that we should be aware of? And directories with no spaces is a very good thing, especially for rasters. And rasters do not like spaces in their pathway. So usually if there's a problem accessing or retrieving your data, that is the first place to look, is to make sure we want no spaces. We'll say it one more time, make sure we all got it. No spaces in our directory. So everybody has that, folks at home, no spaces in your working directory. So week 1 space materials, the bad idea. Now you can say week underbar 1 underbar materials, that's okay, but just no spaces. Had to make sure that was pretty clear for folks so that we don't, that's a stumbling block. So we're all good on that. Wherever you'd like to save that, you can do so, but I would extract those to a file here. And for me, I'll just drop this into week 1, 2001 here. So that's where I'm going to extract these folders or the files to. So DIGA630 underbar WD, that just stands for me, just working drive. The other folder I have out there is for my class stuff. And W1 just for me personally means week 1 and then the year that we're in here now. So I'm going to select extract, but set up your own naming conventions as you desire. Isn't this fun already? Unzipping folders. I do enjoy that too. Yes. Oh, yeah, my Friday nights are enjoyable. Folders and copying, all of that. Yeah, what you bet, any of those. Okay. There we go. So in my folder, in my W on week 1 underbar 2021, I have my grid training folder. Then if you take a look in there, you can see some of our work directories. These are just simple baby sets of data for raster data. They're primitive, they're nothing fancy, but that's perfect. When we want to start figuring this stuff out, we start at the basics, and that's why that's there. So is everybody doing okay on the extraction of those? Okay. Folks at home doing okay too? Yeah, good. Okay. Very good. Okay. Thank you, everyone. So grid underbar training, we download that, then we extract that by right-clicking, extract all to a folder that can, or a directory that contains no spaces. That's where we are here now. Okay. Now, if everyone was able to download the spatial analysis manual, that is great. I'm also going to pull up on the screen for you. I think if I can here. We're going to start off with a discussion of what all this stuff means. If I can find my rotation. There we go. Okay. See, folks in class, can you see what's on my screen? Okay. And everybody, Eric, I think you can see introduction to grid raster. Okay. So what I have next to my workstation up here is a document camera, and I'll be doing my best to work off of that. And then also making sure that my audio is good on the computer. So anybody at home, or if you're in class too, I know you kind of hear me real time and through maybe a delay, maybe. But if my audio trails off in any place, let me know. Buzz me or do whatever it is you have to do. So we need to make sure that everybody can hear okay. Okay, thanks, Devin. All right, so when we think of, the whole idea with rasters is trying to get an understanding of generalized modeling. You know, when we're looking at trying to model, yes, we can do some things in vector with very precision-oriented data. You know, when we think of points, lines, polygons, they're pretty basic most of the time. Would you also agree with that, Heather? Hopefully. It doesn't mean that it's accurate, but its XY location is very, very accurate. So rasters, on the other hand, are a little bit, they're going to be more generic. You know, so we're talking cell size. In other words, if we've always heard that, or maybe many of us have heard of 30-meter cell size or 5-meter cell size or feet or whatever it is, depending on what you have. But when we're looking at cells, we're talking about squares. So that square is representing information. So it's not as accurate as, you know, a point, for instance, like a survey point. Or if you'd had a cell, it's more general data. So when we look at the weather on your phone app, or if you watch the news or whatever, when they give the weather report and they show where it's going to be really windy or how much snow we're supposed to get. Those are great examples of raster modeling, the predictive raster data that we're seeing. It's not super precise. They're going to say up to 4 inches of snow, or, you know, maybe a trace of freezing rain in these bands. You know, so they're not saying it's super accurate, but they're using that generalization of a raster to do that. So when we get into this grid, like we see here, a grid is really a raster. Some of this content that we're looking at here in our materials, this is older ESRI material, but I've yet to find a really good place that gives a good organic appreciation of kind of ground zero content. That's why I still use this book for the content. We're not really going to be using any syntax that's in this book any longer, because that's been replaced now. Because this used to be from the old command line, and, you know, when we pound the keys to code in what we wanted. Now, you know, the software and a lot of those functions do that for us. But the principles, I've not found anything that's bundled up really quite so well yet. That's why we still have these old books, you know. So keep that in mind as we're going through there. So we're really going into the depths of what is a grid, what is a raster. So when I say grid, it means a raster. They're one of the same for us and what we're getting into. So last week in the announcement, I asked people to think about any bit of information that we have is about something that is somewhere. How could you relate that to something raster oriented? I kind of threw out the example there of a forecast. Any bit of information or other ideas that you had. How cool is that though? Folks at home too. Nicole, how cool is that to know that any bit of information we have is about something that is somewhere? I know it's pretty neat if we think of it like that. I mean,
I feel like it makes sense.
Oh yeah, right. Time. Yep. So examples, anyone might want to share? You were giving that some thought. It's
Like,
okay. Oh,
well, I'm just thinking like how topography or landscapes change over time. We can get that from raster information.
So kind of change an area, like if a flood goes through or something and the land changes, erosion, depositional environments.
Or houses are built or not built.
Yeah, and that surface elevation, the DEMs and all that, the raster derived, where you can drop an elevation on each little cell, and then you can start to form slopes and contours from that. And then yeah, rasters you can really dig into by just not only embedding that cell data in there, but then having that relate to the surrounding cells, which then relate to those surrounding cells and so on. So yeah, I see a lot of that mostly used in, the raw nature of DMs, of course, orthos, photography, and obliques and whatnot. But yeah, the photogrammetry on top of vector and the mix, creating a 3D mesh. And then, yeah, just the mosaics you can do by taking, separate raster files and just kind of binding them together to create a larger area. But the analysis, it seems like data analysis can go quite large with raster data, especially when you are creating raster cells from like photo imagery, like satellite imagery, like serious data processing of the RGBs and what vegetation they may or may not represent, and then kind of digitalizing what that color cell might represent as a vegetation or an item on the ground, and then kind of convert that into a representation that item would be.
Yeah, I think
Yeah,
that's
sorry,
great.
just a few thoughts.
Yep. Those are great. It's kind of Tobler's Law in there. It's kind of the other things. And Devin mentioned ground cover data, kind of building on some of the things, Eric, you were saying there. So Devin, great. Or people have ideas in the chat, drop them in there. Thanks, Devin. Jerry, were you going to mention something? Oh, okay. So it's always good to think about this wherever we are. What we're doing is, how can data be represented? Or, some data is going to be better represented as a vector. Some's going to be, could be better represented as a raster cell. And we'll be speaking about that, here a little bit more. So for folks at home, if you have your document there, I'm going to flip down to page 1, 2. So just flipping down. And I'm trying to move our window so that we can see all my writing here too. So I think of a definition of a grid, I think of this like a window screen. That's a simple way to think of that. Or did anybody play, was that like, I always want to say Connect 4, but in a square? Or played that with the Connect 4, you drop like the little, whatever it is. We think of a cell or a grid as a combination of a series, a network, if you will, of all these little gridded points, not points, squares. That'd be the more appropriate way to think of that. And you'll notice that on the graphic here, we have these columns, and then we have the rows that go across, kind of in an X and Y axis that you'll see there. But what's interesting on this, perhaps one of the most important things to remember out of the night, out of our period here tonight, is that what makes raster cells so different from any other type of data is that it has a numeric value. So value is the strength of our raster data. So if you ever pulled up a raster, it's not going to, well, it can have user-defined attributes, but you're always, I can guarantee you're always going to see something in there that is based on a value, number. So the important thing to remember is that each one of these cells may have the same value as another cell, or it may have a different value than a surrounding cell, but all of them will have some type of a value, unless they have no data or something in them. But so for example, let's just say that this cell right here, that might have a cell value of 1, but that 1, the value of 1, the number 1, has a meaning. That's for us incredibly important, never to lose track of. Because when we're working with numbers, those numbers have meaning. And so when we start deriving data off of rasters and we start building things together, when we come up with the end, we're going to have a raster with a number in it. After all of our processing, we still have to know, what does that number mean? So if we start mixing numbers or we lose track of our numbers, that's our role as an analyst, as a technologist, to make sure that we always attach meaning to those numbers. Those numbers are about something that is somewhere. That's information. So we're going to show you some examples of that. The other thing that's important to know is that every single raster, and we'll look at some, or if you're bored tonight after class, pull up a raster, go down to the properties and check it out, or open up the VAT or the attribute table, the value attribute table. All of them will indicate a count value ID or ID count value. That's the other important thing to remember for the night. So right off the bat, page 1 here, these are the two really important things we should be aware of, that our quote unquote attributes, as you see here, for our any grid, any raster, will be, they'll contain it's called a VAT. We'll be explaining. It's like your attribute table for vector data. But an ID count and value. And you'll see that I've added the asterisk by the value here because that's the most important one. We never, ever want to lose track of what that value or that number means, because it has a meaning to it. So actually, let's do that. Let's take a look at this. That might be kind of fun in our workshop. So I'm going to come back over. Just going to minimize our session there. Let's open up ArcGIS Pro, if you would like to do that. Or if you have desktop, you can certainly do that too. You'll be able to see the same thing in the same place. And once, I'll give everybody a second here. I'll pause it and I'll wait for everybody to get their pro session up here. Okay, everyone. I think we all have our pro session up and running. So in a manner of your own choosing, it depends how you want to get in there to do this. I'm just going to open up a new project here, or create a new project rather, and I'm going to call this one, we're going to call this one week. That's just what I'm calling mine here. Week 1, DIGA630 underbar W, week 1. And my location, I'm going to save this one. Save this in my C drive where we talked about our directories, and I think I saved mine here in this DIGA630 work drive, and that's just mine. You can save that wherever you would like. I'm going to drop that right in this W1 week 1 underbar 21. Oh, it's back up there. There we go. Okay, that'll be just fine. So DIGA630 week 1. But again, you can save that wherever it works best for you. Just no spaces in your path name. Well, it doesn't matter probably for your project, but for your data, it should. Okay. All right, so I don't really need this topographic map in mine. I'm just going to remove that. I don't personally need that, but nevertheless, with our map tab going up here, I'm going to add some data. So go ahead and let's go down to our folder that we just added. Need to make sure I'm in the same directory. C drive. I'm just going to where I saved that unzipped folder for me, which is DIGA630, my work drive, and then W underbar 2021. So here's my grid training folder that we asked you to copy over. We're going to go one level into that to grid intro. The rest of these we're really not going to need a whole lot, but let's go ahead and go into the grid intro folder. And we're going to go down. We're probably going to work with maybe 3 main rasters out of this whole data set. And one of them is the L89 Calc 7-G. So it's a L89 Calc 7-G. I was wondering, like, what in the heck does that grid mean? What does that raster, what's the name of it? Let's go ahead and add that in there. Rasters have different names for different reasons. And sometimes a good rule I always like to establish too is have a good name where you have a naming convention for all of your data, whether it's rasters or vector data. Have a good naming convention. Now, for those of us who are just opening up this L89 Calc 7-G data, this is actually river data from USGS land use 1989. That's from when this data was created, land use 1989, from Calhoun Point in the Mississippi River, version 7-G, which was a grid, so, or a raster. So that's what this means. Now, if the raster doesn't show up on your screen, which I suspect it might because of the coordinate system, you know, this particular raster does have a coordinate system. However, it's just not defined. We're going to, when we later on in the course, we're going to talk about data definitions and projections a lot more. But oftentimes what will happen is a data set might actually be physically projected. In other words, it has coordinates, it knows where it is, but the blueprint is missing. I always like to think of a definition of a data layer as a blueprint. So a blueprint is simply telling the house, okay, I know all the dimensions of the house. I know where it is. I know how I'm built. But if you were to have a contractor or something come in and say, well, give me the blueprints. And if you don't have blueprints, it's hard to do any work on that data set. So it has space, it just doesn't know where it is. So to that end, let's go ahead and right click on L89 and zoom to layer. Now your colors might look different than mine, and that's okay. But everyone should see something similar, at least in terms of the features. So we have a raster data set right here. Let's go ahead and right click inside of Pro here. Let's right click on our data set and let's go down to properties. I'm sorry, we're gonna get there. I got too excited. Let's go. That's okay, if you did, that's great. You can back out of there or close it. Oh, I'm sorry. Okay. So folks at home, how are we doing?
I missed the piece of data. It wasn't connecting to my folder, so.
Okay, we'll back up here a second here. So let's go back under add data. And if for whatever reason, if anyone, depending on, again, where you need to save this to, you know, if you can get into your C drive here, double click on your computer, if you go into the C drive over here or whatnot, you might need to, at some point in here, well, for me, it's just showing up, but to add a folder connection, maybe too. I'm just going to pause this here. We'll get everybody squared away. Okay, I think we had everybody caught up there now. And again, folks are trying to add data. Just double check, make sure that there are no spaces in your path name. So I like to sometimes click on this dialog box here and then I can look for spaces in there and I'm not seeing any, and that's good, but we want to be in the grid intro folder. And then all the way down here, we're selecting, just bringing in the L89 raster. That's all we're doing. So bring that in, and then you might again have to zoom to layer, right click and then zoom to that layer. So again, this raster is projected. It just doesn't have a definition. That's why I did not project on the fly to match our base map that we had up. So that's what happened with that. So now that we're in here, Heather, since I thought you were right here, so let's let you lead the charge. If you were to right click on that L89 Calc 7-G raster, folks at home, feel free to do this too. A few people were kind of getting a few things sorted out, so no problem on that. Go ahead and select the attribute table. And this attribute table is a normal attribute table that we're used to. In the raster sense, it's called a VAT, value attribute table, .VAT. Let's go ahead and take a look at this VAT or attribute table for L89 Calc 7-G in there. What are the attributes that you see? Sure.
Well, the row ID, value, count, description. How do I move it? Is that it?
Yep, so we have our ID in there is number one. So let's come over here and take a look at the screen. Oh, not that screen. That's one. So we talked about the count, value, and ID. Those are the three big attributes you will see in any raster that we have. So when Heather was just sharing that out with us, we saw count, value, and we did see ID in there. Here's our ID, here's our value, which is the most important one for us to look at. We're always interested in this value because those numbers have meaning. And in this case, we have a description. This is what's called a user-defined addition to the attributes, if you will. In other words, we just added a column basically and dropped in a description. So you're seeing that there's 4 in there. And you're saying, well, John, you just said that there's always going to be 3 in there. And I'm going to say, absolutely, there will always be 3 value, count, and ID in every raster you look at. However, we can user define attributes, like in this case right here. So what does that mean for us? The reason I was suggesting that as an analyst, it's so important for us to be aware of what those values mean. In other words, what those numbers mean, is we can lose those descriptions. You want to try it? But try, Megan, to lose those descriptions? Yeah, let's live on the edge a little bit. We'll always have the original. We'll always have the original data set. How excited are you all to create your first grid, your first raster tonight? Stoked, feeling it. Okay. We're going to do it. We're going to leap ahead a little bit, but that's fine. Because this is all going to come into play of why we're saying it's so important to remember the ID, value, or the count, or the value in particular. These 3 are always going to be present in every single raster we have. But the minute we perform an operation on it to create a new raster, we're going to lose that. That's what we're going to demonstrate for you. So it all comes back to what we're talking about right here. Those 3 attributes are always going to be present in every single raster. Let's try it. Okay, under the analysis, let's go ahead and up under the analysis tab in your pro session. Whoop, mine's lagging here a little bit. How do I pin that back on? There we go. Okay, so under the analysis tab in pro, go ahead and click on your tools if you want to do that, and you'll see the geoprocessing options appear over on for me, the right-hand side of my screen. If you had your tools dock somewhere else, they'll appear somewhere else, but we're looking for geoprocessing over here. And again, all this is recorded, so if you miss it, you can go back and check it out. But let's go into toolboxes. So in the geoprocessing window over here, let's go to toolboxes. So if you click on that, it's the toolboxes over in the right-hand, for me, right-hand window. And see your toolboxes. Now let's scroll down and let's find Spatial Analyst Tools. So Spatial Analyst Tools. And here we are. So let's go ahead and open that up a little bit there. Just use the drop down and we'll see all these tools, these little clever functions in here that are built in, scripts and whatnot that are going to do cool things for us with our spatial data. Let's come down here to map algebra. Or do we have, yeah, we'll have to go into map algebra here. Let's go into map algebra, because I'm going to give you a different side of this for higher end processing eventually. So it's good to kind of know where this raster calculator is. Think of it as sort of an area for us to build fancy and fun equations. So this is a fun place. So let's start off small, tiny, little baby steps here. Put on the Spatial Analyst toolbox, come down and we're going to open up map algebra. And then let's select raster calculator. Okay, so the fun thing about this, we have a relatively simple raster in here called L89 Calc 7-G, made in 1989, and it consists of river data. And we'll talk about those values again here in a minute, but what we're going to do is simply create a copy of this grid. This is all we are going to do. What? Oh, you're through work. All right, so we just took a pause there, dealing with some license issues. And folks, I suspect if you have it through the university licensing there that we should all be okay with Spatial Analyst, but if not, let me know and I can help you through that. But we'll just have to, I guess, in Heather's case, clicked on the Spatial Analyst extension in the licensing and then it went through. So we're all okay. Okay, so we last left off here. And what we're going to do is show you what happens when we create a raster. So if everybody's with me inside of the raster calculator geoprocessing environment here, we have just a little container, a little area where all of our rasters would be in our table of contents. And all we're going to do is double click on L89, Calc 7-G. That's going to drop this into a box down here. And this is really our processing window where we'll write syntax, we'll write code eventually. Right now, we're not going to do anything too sophisticated. All we're going to do is say, I want you, computer, to take this raster, L89 Calc 7-G, and I want you to copy it and call it whatever we want to call it over here. And I'm going to make sure that, again, that this thing, our working directories, know your working directory, know where all of your data is going. That's a rule. I'm going to talk about these rules early and often. And one of the big rules is always know where your data is going. That's a huge rule. So let's go and make sure that we're going right back into our folder. And you could set this in your environments too, I suppose, here. But we want to make sure that all of our data is going into our into this folder for us. So the name I want to give this, we can call it we'll call it new grid. That's what I'm going to call mine. It doesn't matter what you call yours. And so there, I just clicked in the box here where it says the output raster. So in this directory, again, no spaces, I'm going to create a new grid called new grid. That's the name of the file. That's what it said here. That's just a copy. What I did was, again, double click L89. It's going to drop it in the box. So it's going to take this grid, copy it, and call it new grid. Simple as that. Let's select run now. Okay. So that should have come over successfully, and the unknown coordinate system is recognizing the fact that the resulting output raster does not have a definition. So that's why we're seeing that unknown coordinate system come up. It definitely has a projection. It's a UTM-based projection, but not defined. The original wasn't. What do you notice now in the table of contents over here, folks? What do you notice are for any changes just in the TOC, in the table of contents? Anyone? Mute yourself.
I noticed
Symbology.
that the labels are no longer, for example, open water is showing a number instead of text. And I'm also noticing that the color palette has changed.
Yeah, so the colors are just kind of assigned to that end. But yeah, we're seeing that the open water is gone, the marsh is gone, and all these descriptors. And was that Nicole, were you saying?
Yeah, it's based on the value now because that's what we copied over.
So yeah, go ahead and take the grid that you just created, which would be the new grid, right click on that, and let's look at the value attribute table. What do you see in there that is different? Again, here from your original L89.
No description.
Yes, no description. The description is gone. So I wanted to show or illustrate what happens when we have an original raster layer. For instance, our L89 data, again, these are identical grids. Yeah, the colors are different, but they are the same exact grids or rasters. And it's the same data, but the minute we process on an original raster layer, we can see what happens is that we will lose any user-defined attributes anytime we run a function. This is why it's so important for us to know what that number means, why we know what that value means. We can lose that. So imagine if we're dealing with 20 or 30 different raster layers, You know, I mean, I'm sure we can write a script or something to maintain those and pull them through and join it and whatever else, but just at the ground zero level, know what the values mean. And that's kind of the simple part. But you know what else is cool? You all just created your first raster in Raster Calculator. Is that a natural high or what? My
These
chemistry.
numbers,
What's that, Nicole?
these numbers are not uniform like across, because I've pulled data before where somebody must have run a process because it's missing descriptions or something.
Yep.
And then you don't know what these numbers mean because they're not all common, are they? Like one isn't always open water, is it?
Right here in this case, it should be. Yep.
No, I mean, it's not a uniform
Oh, yeah,
numbering
right.
system
Right.
is my
Yep.
question.
Yep.
Okay.
Yeah, yep. So that's why it's so important to maintain those, whether it's in the metadata or whatever it is, because yeah, you're right. You could think of you could say it's water, but for another person, it could be a ranking system. You know, one might be really bad or one might be really good. You know, what does that one mean? You know, it has to mean something. That's great though. That's a great contribution. Definitely.
The ground cover data that I worked with in Arc Desktop, I had to cross-reference to make sure that certain ground types were what they said they were. We had
Yeah.
different things we cross-referenced just to verify that, yep, okay, all this that's labeled as water is water. you
Yep.
know?
Yep, yep. So sometimes they'll ground truth that to check it, you know, perhaps too. And so it becomes a severe limitation when you're trying to make productive energies occur in a project, and yet we don't know what these numbers mean. You know, that's why to know what that is and make sure that the design you embed in the workflow of that project, whatever that is, that you're accounting for the values, the meaning. So numbers equal meaning. So I wanted to share this with you, that this is why that happens. Whenever we drop or we perform a function to generate new data, we're going to lose that. But we'll always have those three big pillars of support that we'll call our count value and ID, you know, right there. So those are the big ones. So in any event, let's see here. Okay. Congratulations, working with your first raster. So let's come back over to our workshop here and we'll continue on with that. With our little book here, we'll try to get everything in there. Don't worry, we're gonna come back to Pro and have a lot more fun in there. We're just getting warmed up. So in a comparison of vector and grid data, you know, we're illustrating this shortly ago too, talking about, you know, accuracy and precision. You know, what is the difference between vector data and grid data? And we think of points and lines, they're very explicit, you know, in their XY coordinate values, and you know, polygons are really somewhat of the same way. But raster data is, I guess, a limitation of it is that it's somewhat, as the book notes would say, inadequately represented for perhaps a given spatial area. But a benefit of it is that it's really ideally suited for analysis, for spatial analysis, in that it uses locational relationships. I think a number of you before, when we were talking about data and their places and their impacts, you talked about the cells and the points being more related. That's an example of this, those locational relationships. So, you know, here we have an example of vector data, a polygon and maybe a point. And over here, we see that same polygon represented as raster data or grid data. And we'll notice that the exact or the precision of that same data is very different. It's not as accurate, but it could be very or much better suited for that general location-based analysis. And here's a representation of comparing those data formats with the vector and the raster. We'll notice that there's a lot of, you know, kind of overhang here in a few of these areas where the raster cells fall. So some limitations and yet benefits of comparing the vector and grid data. So we think of vector data in our points, lines, and polygons. That's what we're looking at up here, points, lines, and polygons. We have the side-by-side comparison of vector and then represented as points on a raster or a grid. And truthfully, I don't know that I've ever used points in a grid for anything. Maybe some people have. Usually what typically occurs is that people will use vector point data. I think Eric mentioned this before too, but using our accurate point data to generate slopes or elevation from, like LiDAR or whatever it is. We can use points and their values, to build a value-based grid as a result. But rarely do I ever see points represented in a raster or a grid, but it can happen. The other one, of course, being lines. Here's line in vector format to line in our raster arena. And interestingly, the idea of raster-based cells is unique to ESRI in a sense that lines or cells, their benefit is the locational connectivity, or they'll call that the orthogonal connection. So meaning they're side-by-side connection. You're seeing all of these lines side by side. That promotes the opportunity for doing networks, or if you're doing some type of watershed work and you want to see what cells are connected to what, or groundwater modeling. Used to do a lot of that in other times. These cell-by-cell connections, or that connectivity allows that sort of that thoroughness to take place between cells. So it's communicating. So that is a unique process as opposed to really a diagonal-based setup where, for instance, if this cell was connected, this wouldn't share information, just the way that the system is based. It's side-by-side connection. And, another thing to think about too, when I mentioned the points, if we had elevation points, we're generating a new raster from that, is that, data is always a reflection of yesteryear, most times. Now we're getting to the cases where we have almost real-time data, like now, present, whenever we need it. But to be fair, a lot of that is still, we think of it legacy data. That legacy data might be 5 months old, it might be a year old. It's better than 10 years old, but data that we often work with is of yesteryear. And so the whole idea of spatial accuracy always comes in, or should come into our minds for all of us. In other words, we're saying, okay, if I'm taking this line, or for that matter, the polygon, if I'm taking polygons or lines and I'm turning them into rasters, what is my threshold of spatial error that I can really deal with, based on that cell size? And now computers are pretty good with processing, but 10, 15 years ago, if you had to really think about cell size, because if you had a 1 foot cell size, man, your computer would be working for 3 months to try to crank out a small project. So now it's not quite so bad, but still that question should remain for you of what is my degree of coarseness, or what is the threshold of scale for error that I'm willing to accept in that. But anyway, kind of a comparison between accuracy in both platforms. Obviously, vector is better suited for accuracy, and raster more generalized. I'm going to highlight a few of the ways when we take a vector data set and we move it over to a raster, what actually happens? What's that process? And right now I'm on page 1.8 of your manual. And what's going on is what's called a cell-based encoding method. Trying to organize this so we can see that. but we'll work at it in chunks. So on the top up here, we have an input vegetation, I'll call it whatever features here, and we'll see all the fine features that are, presumably polygons in here. And the little squares over here are sort of giving you the idea of what would those features look like if you're going to move it from vector to raster. So this right now, just look at our input vegetation as vector. And the little grids or the cells over that would be how that is going to translate out into raster data. And you'll see in the bottom part of 1.8, this is the default method, or they call it the predominant type method for an output raster. So inside of, whether you're in Pro or desktop or whatever it is you're using, some people use QGIS now, and that's another thing you could use. A lot of those functions are freely available for freeware, but nevertheless, if you're converting features to raster, this is usually the default process. So what's happening is the function takes a look at the first cell as it goes through across here, left to right, and it's saying, what is the predominant feature located in this cell? So yes, we have some here and here that are a little bit different, but the predominant feature type is, whatever this hashing is. So it's going to say, okay, whatever that feature is, that's going to be written out to a value, whatever that in the VAT or an attribute table, that would have some type of information with that would communicate what that is in terms of a value. Likewise, it'll go across, this hash mark and the white with gray, that's a predominant feature. So that's getting written out. So here you could see where that loss of resolution is occurring, but this is what goes on when you're converting features to raster, and where that loss of resolution, or not resolution, accuracy could come into play. You also see some examples that you could look at too during your encoding method that you could set up, is you could say to the software, you could say, okay, I'm going to take my input layer and I'm going to go right to the center of whatever I want, the center of that cell, whatever feature is in the center of that cell, I want that feature written out and preserved. So that's what happens right here, in our middle cell right here, this type of hashing. It's not the most predominant feature type right here, but it's the center of the cell. So therefore it gets written out right here. So that's the center of the cell type method. The last one is more of a weighed features method. I don't know that I've used really, frankly, any of these two, to be honest, but it's still an option. It still exists. But here's where that might be helpful. A good example that might be in the top two leftmost cells. They are not these little, whatever they are, these little patterns right here, the bottom of the uppermost cell and the top of the second one down, they share a common feature. They're not at the center, and they're definitely not the predominant type. However, you might decide that you want that feature to outweigh everything and be written out as the primary feature. And that's what this is showing right here. It's preserving those. So maybe it's some type of a preservation area, or you're working with customers or something, and if a customer fell in an area, you're automatically going to preserve that area because they're in it, or whatever it is. And people have their different reasons why. But the predominant type usually will take a look at the most dominant feature in that, and then write it out to the cell. So that's what happens. Exciting, I know, but now you know how that all goes down. So with applications, I'm on 110, just looking at Raster Applications. And this really is a pretty incomplete list to what's really out there. I mean, spatial modeling with rasters, it's like a Lego set. If you have the right Legos, meaning the data, you can analyze anything. You can build anything off your design, off your workflow. So this is kind of a small incomplete list, but tons of opportunity. And there's a few years ago, someone did an analysis. I think it was, maybe it was for a class project. I can't quite remember. I'll have to look it up here, but she wanted to do a study, a visibility study on ordinances and setbacks off of the bluffs, going down like Highway 35 or 61, like in Wisconsin, Minnesota. I think this project was down by like Lake City or Wabasha or something, where they had ordinances where they wanted to make sure that people are building right on the edge. They wanted to preserve like the scenic beauty, and there's also various types of historic burial sites and things like that a lot of Native Americans used on the bluff edges. And so that was a primary for preservation. So they wanted to, she was setting up basically like a view shed analysis, if you will, from an elevation down along the road. Of course, there's a Mississippi River flowing through the bottom, but at all those points along the road, I think she was just doing a view analysis on this, but for the scenic preservation or something, but see how far back, some of these building restrictions should be. And if I remember right, should have doing something with the local government to enforce those. So it's kind of a cool project. So when we think of these applications, it's not just, it can be 3-dimensional as well. Subsurface stuff like Megan with geology. We did a lot with that, or did a ton with that, and contamination, plume modeling, and all that. But so think about raster modeling when you see it. If you see colorful graphics, you see like these little bands that aren't really super accurate, like, oh yeah, that's raster data. We talked about that. So, but this was really big in the Gulf War. In the first Gulf War, ESRI was really big on modeling a lot of the smoke plumes, figuring out what was going on with a lot of that for pollution, things like that, with the raster modeling concept. Okay. All right. Let's see. So down on 2.4 here, and I wanted to highlight, we're obviously not going to be working with a lot on in this of display and querying, all that stuff. This is just capabilities of raster, but I wanted to highlight the important part where a lot of our work could potentially be with data interpolation, surface analysis, and data analysis. Could put 50 stars around that. That's really where the power of our work is in this arena, is to see things differently that we couldn't otherwise see them, with binary analyses, weighted modeling. I'll probably get to that more next week, but Eric sent out a cool link here. We'll take a look at that. Eric, thank you for sending that. We'll take a peek here.
Yeah, so what this is it looks like a raster data set that is kind of hidden under a vector appearance. But what you can tell is that you're basically tracing a drop of water.
Oh.
And you won't be able to do that with vector, right? So that's where this is a good example of the raster cells that adjoin each other can then go just lower elevation to lower elevation until they reach the river.
Yeah, that is pretty neat. That is cool. I've seen some of these that will go all the way to the Gulf, but this one's a little bit more, it seems like more refined. The other one was pretty, like not exactly
Okay.
super defined, but, oh, so we have to drop it right here in this area.
Yep, so you're just gonna zoom into wherever, drop, and
Yeah, that's pretty accurate.
yeah, and I have nothing to do with the creation of this, but I can only assume that that's raster cells underneath that's really guiding that drop of water. I would think.
Yeah, my guess is that that's a lot of LiDAR data in there. But I mean, even
right. And then with that LiDAR data, then they would digitalize that to cells and incorporate elevations to them.
yeah, like our LiDAR elevation data would be super accurate. That might be like I don't know, whatever it is, it varies for different counties, but like 1 foot by 1 foot cells. So in all those cells will have an elevation, and my guess is that's how this is so refined. But here you can see some of those cells on the Mississippi River right here in this example. So this, the river or whatever it is here, or trying to low pollution potential that we're looking at with all these little blocks on here.
Is it using like impervious surfaces?
Maybe.
'Cause you have like urban versus a park? Or no? Is it just elevation?
Folks at home here, Heather?
Oh, is it not working?
Yeah, we can hear.
Yes, but even like some of the impervious surfaces, yeah, I would wonder if they're, if the elevation would be dropping then, because even those, with those impervious surfaces, right, they have slopes to either storm drains or ditches or gullies, whatever.
I'm just curious if the water drop tends to follow the path, you know, because it would run along an impervious surface, whereas it would soak into the ground at a.
I would think
Right, good
My-
question. I wonder how
my guess
accurate.
would be not assuming infiltration.
Right.
But wow, that was pretty wicked. Look at that one. That one's doing a whole lot of curving and running and going. But yeah, that's cool, Eric. Thank you for sharing that.
Yeah, I always
Good
thought
thing
that
to
was
see.
an interesting one.
Yes, you can drop them. If anybody has some cool things, drop them in the chat. You can take a look at them where we can. But yeah, that's just what we're talking about, the analysis potential of dealing with those little cells. All of that data, I can guarantee, came down to some interpretation of dealing with the high accuracy raster network to get us to that point. That was cool. Okay, so this is kind of cool. It fits in with what Eric was just showing us a little bit. Now this is called the synergy. You know, I kind of, well, it's okay. We've seen more powerful work than this, but we're really looking at really a lot of different layers together. Here we have land use, soils, geology, vegetation, and old ARC info. We're not worried about that. We're just talking about, maybe feature classes or data sets that we put together, whoever used TINs, whatever, into this integrated analysis. And the idea is that they're just trying to give you a sense of how raster analysis can come together by using a lot of different surfaces. And we just looked at the watershed route, for that watershed approach is a cost surface, almost like where does the drop of water go? That's kind of what that really was, following the lowest, just finding the cells with the lowest elevation and was attaching them together. Based upon the rules of our raster line data, what do you see wrong with this? What do you see wrong with that raster layer? Or does anyone see anything wrong with it? Does it look good?
It's just, it's no better than the values you put in those cells, I guess. And then, if you have those elevations that are continuous over multiple cells together, I don't know, then where's the route going? Is now have to analyze which portion of that value in that area is heaviest and go in that direction or not. I know that, if you taken like the LiDAR data and transferring that to raster slope data, which we would then eventually transfer to contour vector data. In the end, those vector lines might look smooth and nice, but they're really being derived from LiDAR to raster information. So
That's right. Yep.
it's so yeah, just like you said, know the data and the values of that, and yeah, as long as you have that straight, that
Definitely
probably
helps.
most important.
One thing that's interesting in looking at this line work, and I always chuckle at this, I laugh at this one a little bit because this was an ESRI publication. And I laugh about this. Is anyone catching this? Just the graphic part of it, the graphics, that if there's anything incorrect with the graphics of this thing? Go ahead and unmute yourself and holler away. Whoever.
So what I was going to say was I'm assuming that this is a river track, and the river's going and then it stops and then jumps over and goes again. Is seems like a physical impossibility, but it kind of almost seems like that's what you're seeing when you're looking at the squares as opposed to, I guess, a picture. That's what's going on in my mind.
Megan, you were going to say something?
I was just gonna say they're not squares. They're kind of angled. But,
Yeah, when we went back and we talked about the orthogonal connection, we talked about the importance of ESRIs to your both of your points here. The side-by-side necessity. In other words, those cells have to be side by side, you know, to make that, like this would not work. This is not going to work in analysis. It can't. And even in the data, the real data wouldn't look like this, because they would have to be a side by side, like there'd be another cell up here. That way this could be maintained. And there'd be one probably here and then another one here. So I was kind of laugh at that ESRI was the proud owner of this, but the graphics weren't necessarily in the same frame of mind as what they espouse the others to be. And
Yeah, it'd be a little difficult to make a network route out of that.
yeah, yep, probably. Yep, probably. Okay. I'm on page 3.2. On page 3.2. And this whole raster data model, you've heard me share this before. You know, it's nothing really super new tonight, but we had the assigning attributes. You know, we looked at that. It's basically our attribute table, this VAT. It's called value attribute table. And if we looked inside of an info file in Windows, we would see a VAT. And that's why when they said why it's always better to use our catalog to move files around. It's so that we don't miss moving the info file with a lot of our rasters. So if we're just going to Windows and we grab a raster layer and we move it, we're like, oh yeah, I moved the whole folder, just said, oh, rasters. We actually missed it because we missed an info file that's stored at the parent level as the name of that same file in Windows. So unless you kind of know what to look for in that, I would say it's better just to use, you know, like catalog or something like that to move your files, because that's grabbing everything together. But let's actually take a look at that, see if we can find a VAT. It's, again, you right click on your layer and open up your attribute table. That's your VAT, but it's stored a little bit differently for our rasters. Let's go ahead and look at that inside of Windows. So right here, you will see that we have the grid training folder. And if I go into that, I'll see grid intro. And a grid intro now, if I go in here one step further, you'll see different types of info files. Now there's a lot of junk in here too, you know, that we don't really need, but you know, here you'll see this L89 Calc 7-G folder, and you could say, whoa, is this the raster in Windows? I could copy this and I could move it. You could say, yeah, you know, you probably could do that, but you may be missing that info file, which contains, well, if we look in there. So we have, these are called like old ARC data files, header files, statistic files. Well, here's our here's our VAT, but it's not notated as a .VAT. But in the info file above there, we should see different, oh boy, this one's going to be long. Oops, get out of there. A lot of info files here. So I wonder if some of these got mixed up. But nevertheless, our VAT is stored inside here of our, in this folder. We'd be missing some of the other like log files that we looked at. So which talks about basically how the layer was processed, what was going on to that raster layer. So moving the Windows version of this, we'd want to be a little bit careful. In other words, we'd probably want to move, the L89 along with the info level file right here. But all parts of the raster, here we have the VAT, a statistics file, header file, boundary, and some other log files there. But that's a little illustration of this VAT and what it looks like. But it's basically in, when we're looking at it in Pro right here, this is your VAT. It's just an attribute table. So nothing more complicated than that at that level there. But the VAT is going to respond differently, and that's what we're going to look at here as we go forward too. It's going to treat data in different ways, with integer data, which means like 1, 2, 3, floating point data, which will be decimal data, and then we'll introduce the concept of no data as well. But at least in our normal VAT, we're always going to have ID, value, and count. When I say normal, we'll be able to look and check out our for our integer data, and we'll learn why the floating point data may not always contain these, but it's for good reason. Talk about why next. Sounds like a lead in to a commercial. Stay tuned, we'll talk about it next. Okay. Flipping over to 3.4. On page 3.4. 3.4. Here, let's look at that. So representing the world using grids, we have a lot of things going on here. And we have a vegetation layer, and we have a roads layer, elevation layer, and some buildings in here too. What do you see that's interesting with that may be different between these layers so far, just in what you can see what's going on up here? Do you have any ideas?
Depending on what you would want to show with your raster, it could have very different outcomes as far as visual effects.
And I'm sorry there, Devin, I had my speaker down there, so I missed the first part of what you said there. If you wouldn't mind hitting me with that one more time. Sorry
I
about
was just saying, depending on which data points you're looking at portraying, it would have very different visual effects.
Yeah, I think it can. What do we want to do with that? Other people?
So just the size of the raster cells themselves.
Yeah, the size of right. Yeah, I mean, it could be as simple as that too. Like, is that what you're gonna say, Matt?
Right. Just like the roads would be more refined with the smaller raster cells, with the larger ones on more of a land cover or a building, and then the design of that might be relative to how much weight you want to associate with that feature, which, as we know, rasters can get really heavy.
Oh yeah.
Yep. So yeah, that type of thing.
Yep, and Megan was asking the same thing there, as Eric, as you were sharing. So yeah, I mean, that was just a quick casual observation. We know that we didn't talk a whole lot about cell size yet, but we're going to right now, and that rasters can all have different cell sizes. They're not always going to come the same. Some could be 10 feet, some could be 10 meters, some could be 25 meters, some could be 5 meters. They all could be different. And that is one important part to note here, is that cell size dictates accuracy for us. And what happens when in this case, what we're doing is we're really putting together 3 different layers: vegetation, roads, elevation, and buildings. We're putting them together to understand reality, or what's happening at that particular spatial location. So when we think of this, I like this graphic because it embodies really what raster modeling is all about. And essentially that is layering. It's a layering concept. So we have different layers, but they are all layered ideally in for a same area. However, some rasters can extend past that of others. And in order for a raster analysis to be truly effective, well, there are different types, I should say that. But this is really, I guess, this particular graphic, we're getting ahead of ourselves a little bit, but is what's called a per cell analysis. A lot of work that we'll do in this class will be a per cell type of analysis. And that means this cell is going to fall in the same spatial extent as these 4 cells right here. And so this cell, this chunk, and this chunk should all be interpreted in the same way. Like the software is going to read what's going on in this cell in the same given unit area as all of these, and compare all these things, what's happening, the values that is together in that same square per cell. So what's interesting though about this is when we have a different cell size, like we're seeing right here with our roads layer, this is smaller. For example, let's say we're dealing with 20-meter cell size. These would be, 5, 10, 15, 20. So these might be 5-meter cells. And I don't know that, I'm just making that up for discussion. But what happens when we actually want to run this in the software? What happens? My normal rule is, I'm going to have a list here, I'm going to pull up here for us to look at, is that it's always rule number 1, on the top of your sheet. You know what, maybe we can look at it right now because it's important. These rules these are the common rules that I like to talk about. The absolute biggest number 1, and maybe we should have done this earlier too, but it's okay. Rule number 1, always explore your data. And you can think, well, explore it. What does that mean? That means everything we can do to figure out what our data consists of and what it doesn't. That way we will know if it's part of our workflow plan, we will know, okay, my data is limited in this fashion. Therefore, I'm going to need to supplement that, or it's going to pose a risk, or I'm going to have to account for it in other ways. So being mindful of what all of your data is and what it isn't. And this ties into that cell size issue that we were just talking about with the roads layer. And we're going to go back and talk more about how cell size, how it's really interesting. Because when we're integrating if we're integrating rasters and all of them have the same cell size, that's perfect. If all of the cells have the same cell size, for the same general area, that's a good thing. The software will be like, oh, this is easy to process. What happens when we have one that's, like in our case with that roads layer, smaller? The way of thinking about that is our output, and I'll write this down so that we'll repeat it again, so don't worry. But our output raster, if we were to integrate all the different types of raster layers together, all different size cells, our raster output will only be as good as our coarsest data set. Because we can't make data more accurate, we can't drive it in. That's why it's always important to retain your most accurate vector layers. Like if you're having points with elevation, that you keep those, because you could derive new data from that, new raster data from that. So it's always good to keep your most accurate data sets as possible. But once we get some of our rules copied down here, we'll go back and we'll take a look at the graphic underneath here again. But our output is only going to be as good as our coarsest data set, meaning our largest cell size, because we can't resample that large data that's 30 meters. We can't go inside of that 30-meter cell size and say, okay, I'm going to make you all automatically. Well, we could say, yeah, I can make you into smaller cells, but I can't make those individual cells any more accurate because we can't go backwards. But if we have a smaller cells sizes that are more accurate, have more accurate information, we can explode those outward to make them into bigger cells, containing more accurate information, but not the other way around. We'll demonstrate that. So rule number 1, explore your data. That's paramount. Number 1, what's our cell size? What's our projection? What's our VAT? Does our data have a VAT? That we didn't quite get into yet. The raster cells, know the meaning. We kind of drove that one home earlier on here tonight. But a third one, always know your working directory. And that implies good file management. Know where all of your data is going. And make sure it's all going to your one directory. You all know where it's at. It's saved. It's safe, hopefully there. And it's organized. So data organization. Another rule is raster names. You know, I think now ESRI might be a little bit more forgiving, but it used to be like 8 characters and it was 10. Now I think it's 13. Might be different now, I don't know, but raster names that are short, but again, no spaces in your directory. You know, so keep that out. We had some examples, surface of those, and we will again, if there's a problem, check your spaces in your directory. So I like short directories, not a lot of complication. They're easy to spot problems. And then the last one that kind of relates to where we are now. I'm careful with this, but it's sort of a good practice, if possible, to try to get all the rasters in the same cell size, if you can. Not the end of the world, but if you can. The only reason I say that is it helps you to eliminate potential problems, or if you end up with a result and you know it's not as accurate as some of your other input data layers, you'll know why that is, because your output again is only as good as your coarsest data set or your largest cell size. Make sense? Okay, let's set that aside. We'll always add rules to that, but let's go back into Pro and kind of feel bad we didn't explore the data, but you know, data is, we can explore that all we want. I mean, there's so many ways to do that. And we did a little bit. You know, we checked out the L89 Calc 7-G. We looked at the attribute table and we looked at the ID count and the value in our description in there so that we know values of 1 if we clicked around in here. You know, and we highlighted an area. So the value of 4, okay. A value of 4 for us will mean trees and shrubs. You know, so, but don't confuse the ID with the value though either. You know, do not confuse the ID with the value. They are different. It's easy to do. Sometimes they could be the same, but most of the time they're going to be different. Just in this example, there's a lot of zeros, 1s, 2, 3, 4, 5, 6, and another one, 1 through 7. So do not confuse the ID with the value. They are very different. Very different. So value of 4, trees and shrubs on that. So, but to that end, let's go and right click on our L89 and let's go down to properties. So right click and then go down to properties. And go ahead and then click that. We have a metadata tab in here that there probably won't be a whole lot of metadata for that. We have a source tab here as well. And that will give us a lot of our information, what I call sort of grounding information for us that helps us to immediately figure out where we are, what we need to know immediately about this. And so for that raster information, let's go ahead and click that. What do you see in there that could be helpful for you as an analyst when you're exploring your data? Go ahead and unmute yourself and share out again, what things of value would you see here?
Cell size.
Cell size. Yeah, so this tells us this is a 5, I know it's meters, but 5 meter by 5, or a 5 meter cell size.
Number of bands.
Yep, well, yep, kind of one straight band, like we're in imagery, we could have, you know, depending on what we had there, multiple bands. How would we be able to check if this is a vector data or a raster data?
Format.
Jerry said format. Yeah, it says it's a grid, a raster, same thing. That's a great way to do it. What's another way we could tell if it's a vector or a raster data set? Not maybe necessarily looking right at this particular layer properties, but we looked at it before. Any ideas? Yeah, Megan said the attribute table. So we had our ID count and value. If we see those, it's a pretty good indication we're dealing with a raster layer or a grid. But cell size, that's also a good key giveaway. Jerry mentioned the grid format. I think Devin mentioned some of the band information. Pixels, anytime we see pixels, you know, we're dealing with that. We're going to talk about pyramid layers here too a little bit later. Well, we could talk about that now, I suppose, before we get off on another tangent. Let's go ahead and talk about if you're ever asked in your ArcMap session or Det Pro or whatever it is that you're working in, you're asked if you were to create pyramids. And this is really what happens is that the software for you is creating what's called an RRD file. See that down here, an RRD file. It's called a reduced resolution data set. We'll be learning more about this in coming weeks. We'll deal with imagery, remote sensing. But for the most part, in simple terms, if you imagine that this whole block here is a raster or grid and see all these like these little individual pixels in here, what that RRD file does is essentially clumps these into larger tiles, just builds them into larger tiles. So it takes, you know, in my case, maybe 6 individual pixels and it groups them into a tile. So that when you redraw or when you draw that raster again, it's going to commit a lot faster. It's just going to pull that tile up. So for those of you who created, if the software asked you to create a pyramid layer, go into your grid intro folder, and I bet you will see an RRD file in there. And to do that, you can go inside of Windows, and I don't actually know if I did on mine. But you see like a .rrd file. If you do find one, let me know. I don't think I did on mine though. Anyone finding any in their files? It'd be not on yours, okay. Yeah, they're hiding in there. They're be like it'll just say like probably the name of your grid with a RRD extension on the end of it. But anyway, something fun you can look at for a later date. This is used in imagery a lot, and some people always said, well, what happens if I delete that? Am I in trouble? And they said, no, because you can always go back and recreate pyramids. It's just a tile that will help you the speed of drawing. But yeah, that's what is happening when you build pyramids, is that RRD file gets created. But you can delete them, you can recreate them, no problem on any of that. Okay. But exploring our data, there's so much in here that when we're looking at our data sets that we can learn about. Is it a raster? Is it vector? Even this spatial reference, right now, this is an unknown coordinate system because it hasn't been defined, and I just happen to know that. But let's look at the extent. So all rasters, whenever we have them, they're different from a vector layer, like a point, line, or a polygon, because rasters are always stored, as you can see on my screen here, with a, now it's given us goofy coordinates because we had to zoom to the layer and it was defaulted in that original map projection or whatever it was for the default map. But we'll notice that there's a top, bottom, left, and right. And this is what's going on when we examine a map or a raster layer for that matter. It's all these top, bottom, left, and right. What that's doing is looking at the max most Y value, the min most Y value, and the min most X value. In other words, where there's a cell, and the max most X value of a cell that's present. So in short, all of our rasters will look like rectangles. Even though they may not appear like that, the actual information that is stored will always be like a rectangle or whatnot, because it's based on boundary information. Like you can't have it's like hanging a screen on your front door. You can't cut out part of it because it's not going to hold. It's going to be, it's incomplete. So any type of screen is going to be like a square type of a fitting. Same thing with how this is stored. So when we think of that, okay, here we go. Trying to get that so you can see it a little better. So in this case, we might only really see data where my pen line is. But in reality, there's a Y max, the highest that this will go up here, and that'll be the upper bounds. But there's also then going to be an X max down here as well, like how we're dealing with X and Y. The farthest we're going this way, highest we're going this way on our Y. But you'll notice that this appears not to have any data in here, but it will. We didn't introduce no data concepts yet, but this would be filled with no data. There's nothing there, but there's still a value there. It's usually like a -9999, like ES or I keeps that like locked away somewhere. But if you've ever been clicking around and found a data set or a raster that has -999 in it, that's no data. So it just means that it's highly unlikely in any raster processing that you will ever encounter a -999999 value to use in your analysis. But there is, or they'll call it null, data might be null. It's just void. But the boundary of that data is still there of your raster. Even though nothing might appear here, those rasters will always have that boundary and that bounding or boundary information. So that's another key component that we could take away from exploring our data. We know that that's going to be square, but the top, bottom, left, and right, that's what that's talking about when it's looking at the extents. So to that end, let's take a look at an example of that with our L89 data. You see this on the top part of our L89 up here, where this area is just kind of this white space? Go ahead and take your cursor and click in there. So if you're having problems clicking, under your map tab here where it said Explore, you have a little drop down there that might say topmost layer. Check to see if that's active, but otherwise, just take your little cursor and click around. And what happens when you click on that? Go ahead and unmute yourself and tell me what you're seeing. And then I'll try it.
I get no data in a pop-up window.
No data? Eric, I presume the same.
Correct, but it is acknowledging a cell exists there, even though you can't see it, so.
Yep, that's part of what we were just referencing, that it's this
No
whole,
data.
it's this syndrome happening. That it would be, we're clicking in there, it's still part of the raster. Still part of that boundary
Right.
information. But it's just not, it's not a value that we assign to it, just null. It's no data, but it's still part of that raster. So go ahead and now let's click outside of that. Let's click outside of the left or right, top, bottom portions of the raster. See what you come up with. Someone unmute yourself when you're ready. Let me know what you think.
No pop-up window comes up.
Nothing. No pop-up, nothing comes up. We're outside the bounds of this raster. So this is a good example that the actual boundary of this raster still comes up higher like this. Just that this area in here just filled with nothing, just no data. It's part of the raster. So do not confuse like a vector data set. If this were a vector, this would all be just vector. This white space wouldn't be part of that spatial area. So always remember that for rasters, we're dealing with kind of boundary or bounding boundary type information on that. So exploring your data, a lot of things we could tell from that. Keys for us for raster data though, when we're exploring a raster, check the cell size, see what the file types are, see what kind of maybe projection we're in, and it'll give us some indication of kind of, where we're at. But I kind of want to try something with you to create some new rasters. We're getting kind of a little bit ahead of ourselves here, but this is fun because I want to show you that we can't, and this comes back to our discussion right here with our grids, that whenever we're doing this automatically, in other words, if we were to integrate all of these layers together, then we'll take a break after this. If we were to integrate all these layers together, and we're to say, ESRI, I want you to run all these processes together. What's happening behind the scenes, we don't know it. There's a process called resampling that goes on. And what that does is it's sort of saying, okay, I know, or this is what the software is saying. I know that our roads layer has a smaller cell size than the other 3 layers that are part of this same analysis model. Therefore, what I will do is resample the cell size of the roads layer up to match the layers, the other layer's cell size. That would be all the same then. That's where we're losing a little bit of that resolution. That's what I was saying in an analysis. You could have 10 layers, 10 raster layers, all with a 1 foot cell size. You're saying, wow, I'm gonna have this really awesome output. Then you might have 1 layer that's like a 100 foot cell size. And your output will be only as good as your coarsest data set, which would be 100 feet, a 100 foot cell size. So I want to demonstrate this to you and give you another chance to have a little work along. Working with resampling some data. So let's try it. Okay, so let's open up Pro again, pull that up, and we can go ahead and remove that new grid that we made. We made just a copy of that. We called it new grid. We just created a copy of L89 earlier. Let's right click and just remove that. Right click and remove, just so that we have L89 in here. Now, what was our cell size again of our L89 raster? So Megan said 5 meters. That is correct. We checked that out. We're going to show you a couple of different ways that you could change cell sizes. And this is kind of a nice little nugget to throw in there for the assignment for next week, because I'm going to ask you to take a raster layer and look at a couple of ways where you could change cell sizes. Here's a little piece that we can always go back to focus on. But with that being said, a couple ways we could do that. Now, one of the more fun ways to try this is to get familiar with our environments window. And right now I'm inside of the geoprocessing raster calculator. So if by chance you were out of that before and to go back into your spatial analyst toolbox, either under the analysis tab, select your tools up here. But if you're still there, we're going to go under toolboxes, open up spatial analysis, and then eventually we'll use raster calculator here. But yeah, we can open up raster calculator. And then under environments, and I guess we could set the environments underneath the analysis tab on your upper right here as well that you're seeing on the screen. But it's easier, we can do that right here in raster calculator. So click the environments tab and let's open that up. Just clicked on environments. And this is where we can start to enforce a lot of cell size change, especially with, we don't need output coordinates here, but our raster analysis cell size, this is a good one for us to look at. Let's say that we want to physically change this. If we create a copy of our L89, let's say we want to change this to, someone throw out a number. Let's do 100 so it's really visible. Just going to type in there in the cell size box. I just highlighted that. Type in there 100. So type in there 100. And then we'll just click off of the box. So we have our cell size of 100. Let's go back to our parameters. So go ahead and click on that, on your parameters next. Now let's go ahead and click on L89 Calc 7-G. We're actually going to double click on that. So in, again, raster calculator here. So double click on L89 Calc 7-G. Now let's go ahead and again, so this is directing me to a geodatabase, and I understand we should probably be going with the geodatabase, but I'm not going to, because there's a lot of other steps that I need to set up for that, and we're not worried about that at that level. But the normal process probably should be if you had a geodatabase, but I'm not going to worry about that. So coming back to one of our rules, know where your data that you're going to create is being sent to. That's where mine is currently on the screen. I do not want to send it there. So I'm going to come back, make sure that my folder is set up here where it should be. And now I can give it a name here, and we'll call this one, I'm going to call it resample 100. Or I'm sorry, not resample. We'll do a resample. I'm going to call mine grid 100. That's what I'm going to call my new grid here. I'm just going to call it grid 100 again. I'm just creating a kind of a directory, giving it a name. I'm going to say I'm going to take L89 calc 7-G. I'm going to copy it, and I'm going to call my output grid 100. Everybody with me? Let's run it. Okay. Jerry, Heather, Devin, Megan, all of us, Nicole, this is pretty. Big kind of grains going on here. Let's go ahead and turn off your grid 100.
It looks like cover art from an old Atari game.
It does. Yeah, or like this. Yeah, the super old Atari. You're right. Remember our first rule. What's our first rule? Our most important one.
Explore your data.
Explore your data. Yep, explore your data. So let's check out our grid 100. Obviously we can turn it off, turn it on, and we can see the difference in accuracy between a 5-meter cell and a 100. So I'm turning that on and off. You can see the pixelation of all these. If we zoomed in on our 5-meter cell, you could definitely see the pixelation. Those are our cells, 5-meter cells. If you were to take under the map tab, if you wanted to measure those under the map tab, could measure these and they would say 5, on there. If you wanted to do that. But now if we turned on the 100-meter grid, you can see it's sure grainy. We lose a lot of that resolution. That's part of our assignment for this week, is to allow you to calculate the loss of that accuracy when you're working with different cell sizes of a area of your choosing. But more on that to come. That'll be a fun one. So explore the data. I'm going to right click on my grid 100. Again, you may call it something else. And the fun part about this is you can delete these grids, your rasters, and you can recreate them as many times as you want. The recording is there. You can practice this again and again and again. That's what's so nice about it. But under the raster information, in our layer properties, I right click and went to properties. What does our cell size show? It shows me 100 meters, and it's obviously visibly evident. Obviously our format is grid or raster too. It's visibly apparent here for us too. And but we're definitely seeing a clarity of cell size resolution. I want to show you another way that we can do this. Before we go any further, I'd like to have a discussion on our environment. So if everybody can go click on that environments tab again in your raster calculator. Again, this is all new, so try not to, we're going to see this for the next few weeks. We're just introducing some new things here, but when we enforce a setting, we need to make sure we turn it off. Because anytime we run any other processing, what do you think will happen with that cell size? Yeah, so Jerry said it's going to go back to the last input setting that we had in there, which was 100. So for us, we're going to set this back to the same as L89 calc 7-G, which is 5. That was a 5-meter cell. If we said maximum of inputs, what would that be? It could be 100, whatever the raster layer is that has the largest cell size, it's going to go to that layer. So we're just going to go back to same as layer L89. Oops, okay, there we go. I just want L89, need all that complicated stuff. But so now we should be processing same as our L89. Another way that we could change that cell size is with a tool called the resample function, or resample tool. And I'm trying to expose you to different ways of thinking about this. This class is a lot about, like, I don't expect you to know what resample is. I don't even expect you to know how to set cell size in the raster environments window. You know, the reason that we have these different classes are so that you can experience them and maybe try to remember them. Like I said, this class, we used to have an entire semester, 16 weeks on just this stuff, not imagery or anything else. And it is incredibly vast. And I mean, we could have a course on it probably, and all these tools and functions and higher order processing. We're trying to give you the baseline to know what's there so that you can go in there and check them out. But anyway, I'm going to come back out of my geoprocessing area here. I'm just going to say back. And I'm going to, I think, next search for a tool. So I just went back to the main geoprocessing, and a tool or function, whatever it is here, I want to introduce to you to is called the resample tool. Why am I talking about the resample tool? Because I'm showing you what's happening. If ESRI, the software, resamples these small little cells upward, the resample tool is, for the most part, what's happening. It's resampling these cells upward to match the other layers. That's why I'm showing you what this tool is here. So resample changes the spatial resolution of a raster data set for basically working with rasters. So let's go ahead and open that up. And this is pretty easy dialog prompt here. What we're going to do though, remember before, it's not really a rule that I was sharing, but I was saying if we were to integrate all these rasters and you had a lot of them at different cell sizes, we said the output of your raster or your output raster will only be as good as your coarsest data set. We're going to test that. So what we're going to do is we're going to take our 100-meter cell raster that we just copied over. In other words, that's the big grainy one you see on my screen right now, the grid 100. So we have a 100-meter cell size there, and we have our L89 at 5 meters. We're going to try to take that 100-meter raster, and we're going to try to force it to be more accurate. So we're going to try to take this big grainy thing, and we're going to try to turn it back into this. Force it to be more accurate. As an example of the input of your output data, your output raster is only going to be as good as your coarsest data set. It's part of a resample. So input raster, what should we put in there? Grid 100. We want our big grainy 100-meter cell size in there. That'll be our input raster. Again, what we're going to do is resample this. We're going to tell the software, okay, software, I want you to go to this 100-meter cell raster, and I want you, software, to convert this back into a 5-meter cell size grid, a raster. And I want you to make it as accurate as you can for data and everything. So let's go ahead and, again, we'll make sure we save our data out into know our working directory. For me, it is a simple path name, no spaces. And I'm going to say, what do I want to call this? I'm going to call it resample. I'm going to name mine resample 5. I'm going to resample that 100 into a 5-meter. I'm going to call it resample 5. Whatever you want to call it, that's fine. Resample 5. Okay, so what it's saying, we have our input grid, 100-meter cells. We're calling our output new data. It's just like creating a new layer. We're calling it resample 5 for a 5-meter cell. Output cell size. See, it's default to the 100. Let's go ahead and put 5 in here for the X and 5 for the Y. So when we look at cell size, it's just measured by an X and a Y. So from a conceptual standpoint, if I just go back to the DocCam over here, this is what we're doing. We're resampling a 5-meter. We can go upwards too. we're going backwards. We're going from big to small, but you can also go from small to large. And usually in an analysis, this is typically what happens. You never go from large to small. You always go from small to large to match your course's data set. But that's what's happening in a typical resample when the software does that. It'll move everything up to your course's data set, which in this case is 100. That's why your output will be really grainy and not as accurate, in quotes, so to speak. But that's what resampling is doing. But I was also mentioning the cell size when we're looking at our input dialog. Cell size is a function of the length and width, really, of a cell. So 5 meter by 5 meter. And if we were to count the area of a cell, a 5 meter cell size raster, if we looked at it per cell, an area of that would be 25 square meters or feet or whatever it is that you had. So if in the activity or the assignment for this week, I'll ask you to calculate the area for your largest value. And this is one way to calculate your area, at least of one cell. But what we would do then is take our area, which is in this case 25 square meters, and we'd multiply it by our count. So the number of those cells that had our biggest value. But more on that to come. Don't worry too much on that. Getting ahead of ourselves a bit. Sticking to the basics right now, which is how we determine area. Well, just length times width of a cell, our cell size. So let's come back over to our geoprocessing window. So we're going to take that 100 meter cell, we're going to force it back into a 5. Megan, what do you think? Is this going to work? Megan said she'll think it'll work, but she's not sure if we're going to get a lot of the original data that we have. Let's run it. So the coordinate system, that's fine. We know that is an issue. I'm just going to minimize these so we can see them all together. Let's turn off all of them. Let's turn on our L89. That's our original. So I just turned off all my grids, all my rasters, just have L89 on. Now let's turn on our resample 5. So my top one that I have in my screen is the 100 meter cell that I tried to resample and force it smaller to make it more accurate to look like L89. There we go. However, let's explore our data. What do you have for a cell size for anybody that looks at that? Unmic yourself and let me know what you find. Explore your data.
Cell size, I am showing 5.
Cells,
Correct me if I'm wrong, but we still have a block that theoretically is that same size, but now instead of being 5 by 5, we've correction, it went from being 100 by 100. It's now, we're just saying it's.
yep, I know what you're saying with that. And this is exactly the dilemma.
It still looks like the same block, but now there's more of them in there.
Let's zoom in on that. So what basically just happened here is this is a prime illustration of that. Yes, we can take that 100 meter cell size. We can force it into a 5 meter cell. Like we can break it down.
You guys are
5 meter cells.
echoing.
But it's not going to make our accurate. What?
You gotta turn your.
Oh, sorry. There's a little bit of reverb here with.
Oh, sorry about that.
Thought I was at a
Yeah, there's
concert for a
multiple
minute.
sounds going on here from muting, so we're trying to mute and hear every. Nicole, did you have a question?
Oh, I was just saying it sounded like I was at a concert for a minute.
Yeah, sorry, guys, everybody gets excited to talk and
It's okay.
that's like a rave party in here. But, okay, so yeah, what's basically happening here is we're taking a 100 meter grid. We can turn it into 5 meter cells again, but we can't make the original data more accurate. Like because it was only a 100 meter cell to begin with, we're just taking all those values, or we're taking the value of that 100 meter cell and we're just putting it all in the 5 meter block. So if we zoom in on that, if you're to select, if we can kind of get in there far enough here, like if I, let me find a 5 meter. So here's a 5 meter block right here. And now if I turn on the resample 5, should highlight here somewhere, but. So what's happening inside of all this, like on my screen, for instance, in this blue area or green area in here, these are all going to be, 5 meter blocks. So it's 5 meter blocks, but the input data, like if you took this 100 meter cells, this is just going to be full of little 5 meter blocks, 5 meter cells in here. That's what's happening. So we shoehorned it back into a 5 meter grid, but the data itself then isn't any more accurate. That's why it's always good to always keep that original high accurate input data sets, whatever we have, because we can't force data to make it more accurate. So that was the whole purpose of that, to show you that what happens with resampling, usually goes upwards, but we just try to force it backwards, and it really can't work on that. So let's take a little break. Would that be okay? Or do you want to keep forging ahead? Okay. So we'll take a little break. And all right, welcome back from break, everyone. It's always good to take a break. Get a chance to visit with each other and or take care of some things at home or wherever it is that you are at. So we just spent some time looking at 2 different forms of changing cell sizes, and one was the resample function. That one could be helpful for you in the assignment for this week. We also looked at setting the cell size, really just kind of doing an override in environments here in our geoprocessing window. Where did that go here now? Oh, I have to go back to, I'm in resample. I need to go back to my raster calculator. And that's where we could, where we were able to change our cell size to, one case we did 100 in our case, but you can certainly change that there too. So there's a couple places where you could go for some little assignment reminders, but did want to talk a bit about what this all means with respect to, we talked about our VAT before, value attribute table, and I'm just going to draw a grid here and how this count and ID, how it all relates to each other. And just to give you an idea of what this all is. So I'm just going to call this, and I'll put this on the doc cam here in a minute. Grid 1, we'll call this our grid 1.VAT. So move this window out of here. So we have, we're going to be talking a little bit more about this, but did want to interject that here because we are talking about a lot of cell size, and we've talked about our ID count and our value. And so each one of our cells are going to have, cell size. And this grid happens to be just grid 1, it's just a random name I gave this. But these are all the values. All these values should mean something to us. But I wanted to illustrate in our VAT or value attribute table, how would all this look? What does this mean? When we have values, and how do we account for it in our attributes? And so how many values do we have in our grid 1? If anybody wants to unmute themselves and share out, how many values do we have in there? List them out for me. Anyone? Go ahead, Brandon.
0, 1, 2.
Yeah, so we have values of 0 and 1 and 2. Here we have values 0, 1, and 2. Now, what's the count of those? We're talking about calculating area and things like that of cells. That's kind of why I'm bringing that up here now. But our count is especially important when we know that we have so many values or so many counts of cells that have, for instance, 1, a value of 1 or 2 or 0 or whatever that is. What's our count? Let's see here. Megan, you're getting ready to just
For 1 or for 0, 2.
Take them all. What's our value or what's our count for 0? Are you unmute, or go ahead and unmute yourself there? Then people can hear at home too. It's fine.
That's 2, right?
So we have a value of 0 and a count of them, we have 1 and 2. What about for values of 1?
1
Yep. What about 2?
and 1 again.
Perfect. So that essentially means for us that, you know, where the count is valuable for us, and that if we were going to, let's say, generate an area, if we had a 5-meter cell size or a, you know, a 1-meter cell size, and we wanted to get the area, this would be, you know, 1 times 1 for 1 square meter. We'd multiply it by 1 for the count. So our total area in this grid would be 1 square meter. Yeah, that's one way of thinking about using area. So we can calculate area by way of cells too. But again, we'll come to that. Again, I'll give you another example as we move forward. All right, so good work on that, everybody. Let's go ahead and flip over to 3.5. I'm sorry, 3.6. Page 3.6 on our document. So I want to chat a bit about continuous data versus discrete. So continuous floating, meaning, you know, really a floating point, and discrete really being that of integer data. So, and the drawings that I've been making for you on the piece of paper, those have all been discrete or integer-based values, like 1, 0, 2, you know, that those are all integer-based raster scenarios. And here we have another one. So discrete data or whatnot usually use integer-based grids in this case, and they're used to reflect very clear some type of a very clear specific, I'll call it land feature. You know, in this case, little buildings here, this might, or a residential or whatever, this might be a farm, this might be woods or whatever it is here, this might be industrial. And you can see further down on the page a key for that, or a legend. And we'll just pretend that, you know, on here I have an example that these might be 10-meter cell size. So what would our area be if we were actually thinking of each cell, if we knew that this was a 10-meter cell size?
100 meters squared.
100 meters square. Yeah, yep. And so we had 10, just writing that down. So we had a 10 by 10. Yeah. So I think it was Devin that said the area of this would be 100 meters square. If you know, that was a 10-meter cell size. And we're going to pull up some examples here to look at. Just a minute. But take a look at the values. Remember, we said one of our key rules, know what the values mean, or the numbers will have a meaning. So numbers or the value has a meaning. This is what the meaning shows for us right here, that values of 81, which, let's see, you may want to look on, mine keeps focusing in and out here, this doc cam. It looks like 81 is really up in these 6 blocks up here are values of 81. So that's an industrial area, and it makes sense because we have industrial below. And agricultural, 37. So we see our agricultural areas right here, 37 here. And then we have our residential of 41 right up here. And then 22, looks like 4 cells of 22 as forest. So like we did before, I have a little value attribute table that I built up here for you, the VAT, for what we were just looking at. And so what would so if we have values of 81, 37, 41, and 22, I have the counts in there for you of 6, 6, 4, and 4. We just kind of went over those, 6, 6, 4, and 4 of each for, you know, 81 and 37, 41, and 22. So given the fact that we have our, let's say, what was 81? 81 was our industrial area. Knowing what we know with our cell size of 10 meters. So if we knew our area, know your cell size, part of exploring our data, you know, but in this case, we can't really explore because we don't know. So I'm just kind of making that up. But let's say we were to add a user-defined area area column into our VAT. What would our area be for all of the cells that have a value of 81 that have a count of 6? If we know that each cell has an area of 100 meters, what would our area be for industrial, which is 81?
600 meters squared.
600 meters squared. Okay, Heather, you're on the right roll. Let's keep it going. What about for 37 here, which is our agricultural?
Also 600 meters squared.
600, and Heather, take it all the way here.
And 400 and 400.
So 400 and 400, and all being that, you know, our each cell 100 meters, and then we're just multiplying to get our area. We're just taking the area times the count of those, or the number of those will give us an area. So we know that for our industrial and our agricultural, both represent the greatest area on our, just with the overall count. So now we're able to say, okay, given my cell size, I can say that these areas of industrial and agricultural each represent, you know, about 600 square meters, again, assuming the cell size is 10 meters. And so that's a handy way to use your rasters to calculate area. Area of a cell times your count. Area of each cell, or of a cell, times the count. That's kind of what we're doing to get total area for a value that you're interested in. So that's a fun one to do. Area of a cell times the count gives you total area. And so as we're looking at, you know, the integer type of VAT that we looked at in this example right here, they're always going to have a value attribute table because they're integers, and all integers will have a count. They all will have a number of unique integers. In this case, 6 for 37, for instance. And if we look and discuss now on the opposite side, so far all we've looked at is like our L89 data. And our L89 data was all integer. It was like 1, 2, 3, 4, or whatever it was. And opposed to that of continuous data, or what we'll call floating point. This is where it's going to get a little bit tricky. So our rasters are going to be either integer, or they're going to be floating point / continuous. So floating point grids or rasters tend to handle VATs, well, differently. Let's show you what that means. Let's go into Pro, ArcGIS Pro. We're going to come back to this. We're just showing you right away. We're going to show you an example of continuous or floating point data. Examples being elevation, slope, precipitation, temperature, all continuous, all floating point based. Let's go into Pro. And it's okay. Let's go ahead and remove. I'm going to remove resample 5. I'm going to remove that. I'm going to remove my grid 100. So all I have in there, I'm just going to zoom to layer of my L89 Calc 7-G. That's all I want in there for right now. Just my L89. Let's go to add data, and let's add in there inside of, again, our grid intro folder. So again, we're in our grid training folder, or wherever you save that. Once you get into the grid training, we're into grid intro. Let's scroll down and we're going to find this grid called Cal Topo Grid. So topography, elevation. It's a great example of continuous or floating point data. Let's add that. So this might be, again, a slightly different part of the Mississippi River here. So you may have to right click on that layer and say zoom to layer for right now. This is bathymetry data. river bathymetry data. So like a boat with, sonar recording elevation depths in and along the river. What's our number one rule, everyone? Folks at home, folks in person, what's our number one rule? I just heard the echoes in this classroom.
Explore the data.
Yeah,
Yeah.
man, this is what we want to hear. I can just hear that, the reverb in my head. Explore your data. Let's do that. Check out your data. What's it saying to you? Again, right click in properties. So we're checking out raster information predominantly right here. What's our cell size? Megan and everybody else in here said 5. Folks at home, you're probably saying 5. We know that it's a grid. You can see that. The pixel type. What's going on with that? This floating point. That is going to tell us that this is a continuous or floating point raster. So if somewhere on an exam, someone were to say, take a look at this data set, how would you know if it's a floating point or a integer based grid? A lot of ways you could tell this. Here's one way. If you said provide evidence of that, well, you could show this. But there's another way too. You can see that in the table of contents as you're looking in on the left-hand side over there where it says under CalTopo grid, where it says value. Anytime you see that, those stretch bands, or you see that gradient, like color scheme going on, we can almost guarantee that's going to be a floating point or continuous type raster, but you can also, of course, see the decimal values in there. Perhaps one of the biggest giveaways, if you will, right click on CalTopo grid. Open up your VAT. What do you see? Shout it out, unmute yourself so everybody can hear at home too. It's fun sharing this with our community folks, people at home there or work, wherever you are. Shout it out. What do you see when you open up your VAT?
No attribute table.
What? What? Jerry, there is no VAT with this. Devin, there is no VAT. Maybe it's my concussion that I had recently, but I don't see a VAT in here either. I don't see one. It's grayed out. Attribute table gone. What's happening with this? Anyone want to venture a guess? Unmute yourself, shout it out. Here's what's happening. Here's what's happening with that. Oh, Heather has her.
You'd have to have a specific point to have an attribute. So if it's floating, you wouldn't have a specific point.
Go ahead and click on one of those. Go ahead and click on a cell. Zoom in, zoom around on this thing. We have a 5-meter cell, and you can see that as I get zoomed in here, you can see these little pixels. Those are 5-meter cells. Click on one of them. So each cell does have a value. A lot of decimal places behind those, however. So each cell has its value. So Heather was onto something with that, if I were to take it a little bit further. The challenge with continuous data or floating point data, the odds of trying to maintain a stable VAT with your count is going to be crazy. It's ridiculous. So how many cells in here might have the value of, at least what I'm looking at on my screen here, 418.933838. There might be 4, might be 5. Your attribute table is going to be about 15 miles long. So the idea is for floating point, it's another good way to check this out if you're ever not sure and you're like, what? My raster doesn't have a VAT. What's going on? Am I doing something wrong? No, you are doing absolutely everything correct. Continuous or floating point rasters will never have a VAT because of how it can't be organized to show an ID, a count, and a value. Well, it have a value, but the count, trying to organize the count for all those, like click on some other cells around it. they're also radically different. So to try to come up with a count for all those it's just not practical. So what we usually do with these types of rasters is we use them to subset out data. Next week, I'll be working with you on subsetting or taking data out, and how do we do that? So a lot of different things to think about with that. So our raster data, our VATs, we're gonna have VAT with integer data, but not with continuous data. Just, we won't have that, so something just to be mindful of. And also with we kind of talked about the VAT here as well, and the arena of no data as well. We'll be seeing no data again too, but really what's happening with no data in our VAT is it's still there, but what we're seeing is that, this is just another sample of a grid 2 here, but we have a couple cells with some values in it, but no data is just a large negative number. You might see that as like a negative 9999, but a value and a count, we're just going to see here's a value 1 and 2, but the count is just 1 and 1 of each, but the no data is not actually included in any of that analysis. So when I say what happens when we encounter no data in our rasters, this is what's going on. So let's say you have 2 grids. Now, when I have these laid out, it means that they're actually stacked in the same spatial extent. So this is an example of a per cell analysis where grid 1 sits right above grid 2. And we're going to add the values together to form what's called an out grid. It's just a random name. We could call it whatever we want, just a title. So this is a simple operation. Oftentimes when we see the add sign in here, this is a great example of suitability modeling. We'll get more into this next week, but I want to talk about how no data gets brought into the equation here. And that is, so if we have grid 1 and it's a per cell function, again, remembering that these are stacked. That's what this is implying here. So cell 1, or the cell right here that has a value of 1, is directly over the top of grid 2 right here. So if we were to add those, that's what this means, is we're just taking 1 plus 1 and writing the output to the same corresponding cell to 2. So again, this is great for examples when we are trying to enhance we can add weights to this too, but when you're trying to figure out, let's say you have a ranked model and you have a lot of 1s and 0s, or 1s are really good data, 0s are not, and we add up grids. Like if you had 10 grids in here, your end output will be some type of a ranked numeric set where the higher the value will be the more ideal area, perhaps. I'm not saying that that is the case here. I'm just showing you what's happening in a basic function where we add grids. So 2 plus 2 is 4. Now here we have 0, which is a value. 0 is not no data. 0 is a value. But if we take 0 plus no data, the output will always be no data. So that's how no data gets brought into this equation. So conceptually, that's what these things look like. 1 plus 1 is 2. 2 plus 2 is 4. That's kind of this overlay concept that we're referring to. All right. So we went through the VAT a little bit there, and let's jump to 316. Page 316. Might be a few pages over, just a few pages down. Where we talked about no data a little more here. The concept of no data, really what I was trying to highlight there is that the output is no data if any of the input cells are no data. And that was a good illustration of that process. So no data can be a pain in the backside, but it also can be a good way to protect sensitive areas if you don't want that factored into a design or a model. One common way we can test a raster for no data is by running something called, it's a test actually, just called, I think it's called isNull. And so let's try it. I'm not actually sure here. Let's see where we can find with that. Just going to turn off my Cal Topo grid here and turn on my L89 and zoom back to that. Zoom back to my L89. Okay, we're gonna, or yeah, it's called isNull. I think it's isNull. So we're gonna try to find areas that are null. And I don't know if that is in my raster calculator tools. There's set null where we can set values to no data. Let's see if there's a isNull test. Okay, there is an isNull test. Trying to remember off the top of my head the syntax for this, so you have to try this with me. So we know that when we were clicking around in L89 here, we know that there's no data in the upper part up here. But let's see if we can run, let's see if we can run this. Let's say we wanted to, I think it's, I'm trying to remember here, isNull. Let's say isNull L89 calc 7-G. I think there's some parameters we can put on the end of this. But right now, let's just see if we can write this to an output layer. We're going to call this one isNull demo. Just an isNull demo. Let's see if there's. I have that here. Okay, yeah, so if we run just something called isNull L89 calc 7-G, it's saying I want to find all the null values or no data in L89 calc 7-G. And when you find those, I would like you, software, to write that out into a new raster that I'm just calling a name, and I'm just calling it isNull demo for a demonstration. Let's run it and try it. What this should do, if we have this set up correctly, it looks like it did that for us, is it returned true values to 1 and false values to 0. So why would this, or how could this help you? Unmute yourself and chime in. Nothing super complicated. Just an example of an isNull. It's to show you, for the most part, where your data is null, where it's void. Eric, go ahead.
Yeah, so there's, I assume the zeros would just be false, and that would be the no data. And we can then maybe just extract that out. So we're now dealing with just the relative data of 1, or actually opposite in this one, it looks like.
Yep. So our ones are the, when we set
so yeah.
something, we said is null, we're saying for where is it null? So that'll return
So
a value.
the ones would have a null value, right?
Yep, correct. Yep, ones are going to be the ones from our L80. The ones here are basically showing us where there was no data in our maps. But now in our isNull map, these are literally now, I can pull that up. Oh, get the screen out of the way. We now have values in place of that. So we have 1s and 0s here in our isNull value attribute table. We have our ID count value. So our values are 1s and 0, but this is a new grid. So the new grid is showing us where areas in L89 were null or no data, just where there's nothing. So all this was a test to see where in L89 those data were, where it was just null, where there wasn't anything. So you're right, Eric. Yep. So that was a fun. Oh, someone.
Could you use this for like the area of where you don't have data?
Yeah, I mean, sure, I think you could. You could probably run a test. I mean, it depends how you'd set it up, but yeah, you could figure out exactly where the areas are just null, where you don't have anything, so that, you know, for me, if I don't use this a lot, but I would probably suspect you could use that, Nicole, to say, all right, if I'm going to run an analysis, I know right now I'm going to have null data in the top up here. And so when we run this, we're not going to have any data here. Now we could change that. We could write this to something. We could write it to a value of 0. That's the beauty of rasters. We can change data and we can set it to whatever we want. But we're getting to that point, to be able to do that. But we could try it. We could try this. I'm not sure how it'll work, but we could try this to say, like with our null data, we could say we want to, there's a command that we just looked at in there called set null. I think it was set null. Yeah, let's say, here's an example of, well, number one, Nicole, to answer your question, we would use a function called reclassification. We're going to get into that next week, where we reclass our values into something else that we want it to be. So we can change this, these values if we want it. But let's say we were, we're in this grid here, and let's say we want to, right now we have values of 0 and values of 1. Let's say we want to change the values of 1 to no data here using our isNull demo. So let's try that. So now we're actually going to set our values of 1 in this grid to no data. We'll try it, see how it works. So this is a good example of saying, let's say you want to protect data somewhere. Maybe it was endangered habitat or forestry or customer areas or what have you. You just want it to be null for privacy or whatever it is. Here's how we could do that. Let's give it a whirl. I'm going to clear expression. And obviously we'll put a new name in here, but let's say set null. So we use a set null here. And let's say we go to our isNull demo that we just created. We want to, in my case, turn all of the green or tan areas up here. We want to convert that to null, like set it to no data. That's what we're going to do. So we're going to say isNull demo. We're going to set null values in this grid that we called isNull demo. Let's see. Now we're going to introduce a new operator here for you. This is called our double equals. And what that means, it's a test for equality. And it doesn't mean equals. It means a test for equality. And I think we can get this right. And I'll have to probably write this out for you here, sketch it out so you kind of see what we're doing. I'm just going to make some notes here as we're putting this together. Give me a second to jot this down. Okay. Okay. I think we called that isNull demo grid. Okay. So this is what we're going to say conceptually right here. We're going to say set null on my computer here that we're watching. Set null all the values of our isNull demo grid where they are tested and evaluated for values of 1. So we're looking at this tan area or whatever it is, green area, whatever it's showing up. So all the values of 1, which is this. So where that is true, where those values are true, where those values were tested and evaluated for 1, then let's write, we'll write that, write those values of 1 to null. So that's what's going to happen. Otherwise, let's go ahead and replace it with our value. And we could do this for anything, really. We could replace it with the same values, or we could replace it with our L89 values too, if we wanted, if it's false. Well, we could try that. So, and this is where the fun really begins to take shape. A lot of the syntax we need to watch carefully too. Okay. Let me make sure this actually works here for us. Don't worry too much about this syntax. I'm going to put a Word document up there for you next week with a lot of these different options so that you'll be able to see this and record them. And, you know, these are just introductions to how we can start managing or looking at data in different ways. And so I'll make this a little larger here. But that's what I'm going to try. So what this is saying, we're going to create a new grid. That's a function of, we're going to set null from this grid right here. All the values that tested were evaluated for 1. Otherwise, we're going to write those cells that didn't meet that into L89. So in theory, what should we end up with? We should end up with our original L89. That's what we're kind of doing. So it's always good to kind of think through those steps. It's kind of like the bouncing ball in Sesame Street. You know, each one will have a different, you know, thinking through this is good. Let's give this a new name. We'll call this one set null demo. And let's try it. Hopefully this will work. I think my syntax is good. If there's spaces or missing parentheses, it'll let you know. Let's run it. Okay, so that looked good. So Megan said that we should be right back to where we were. And lo and behold, if we turn off some of our layers here and start to compare other, you know, the colors are going to be different. But I mean, if we take our isNull demo and we have only that turned on and we select up here, what should we expect to find? Yeah, so people are saying nothing or no, well, no data. Yeah, no data. And lo and behold, there it is. So no data out there. So kind of a fun activity to show you how you can start to control parameters. And I introduced you there with this set null process. We're gonna, before we leave tonight, I'm gonna introduce you to the condition statement. And this sort of builds upon what we're doing here now in that we're writing conditions that we want for different data. Right now, we're just working with one raster layer. So what I mentioned before in Raster Calculator, we can add a lot of different layers in there, rasters, and do a lot of complicated, I'll call it equations. You know, this is pretty basic, but it's a good introduction in when we start to work with different types of data. But again, please do not feel overwhelmed with us. We're going to get a chance to go through this in more detail in weeks to come. But this is what we were doing in that process. So if I can graphically explain to you what we just did in a sense. So we had our isNull demo grid. And when we wrote that syntax for that, we said, I think it was set null. We had 2 parentheses. We said then we wanted our isNull demo. This is our grid. This is just the name of a grid in parentheses or quotes, where that grid was tested and evaluated. You know, that double equals again is an evaluator. Where it's tested and evaluated for, oh, wait a minute, did we do set null? What did we do here? There's too many set null is null, I can't keep them straight. So where that was equal to 1, because we were interested to begin with in turning these values of 1 in our isNull grid, we want to turn those values of 1 into nothing, into no data. That's what we were doing. Where that was tested and evaluated for 1, then turn those values of 1 into null, into nothing. Otherwise, we had another comma or a parenthesis, order of operations, you know, just for that. Otherwise, if that didn't meet the evaluator and it wasn't equal to 1, which pretty much means 0 for us, put everything, write all the values of L89 calc 7 -G, and then an end parenthesis, so that we have our parentheses in check and all that. So when we went through that, here's our original raster layer. So wherever that was tested and evaluated for 1, we are going to write out into our set null demo grid here null values. So help me out. We're looking for where all the values were tested and evaluated for 1 from our is null demo grid. So what are we going to have right over here in our output grid? This is our output grid that we just created, our set null demo grid raster.
No.
Null. So that's going to be no data because it was 1 right here. What about 0?
We'll revert back to
So we have our L89 data, which is down here. So what is the corresponding cell? Now, again, now all these are spatially overlaid, so per cell. So all of this cell overlines with this one and, you know, and this one here. So what are we going to have for 0?
7.
7. Yep. So if this was anything other than 1, let's write the original L89 data to that. So here, this was 7. This was 0. It didn't meet 1. So 7 is going to come right up here. What about here?
4.
Wrote the false value. So it wasn't equal to 1. So therefore, we're going to write in here our L89. And what about over here now? Here we have 1.
No data.
No data. So that's graphically what, you know, in a conceptual way, what we were just doing there. So honestly, I don't know that I've ever really had to do this. It was just kind of on a whim that we practice it here in class, but to show you what are ways we can change data in very, call it, I don't know if I
This
call it-
video is pretty cool with like trying to take out water, or like if you gave an example earlier, if you didn't want to include a portion.
this is a way you could do that. Yeah.
Yeah.
If you had, let's say, some unique customer territory or a habitat, some, you know, you had critical habitat or whatever it is, and you wanted to omit that from any analysis for whatever reason, this is a way that you could change those values, you know, like we did with our, right here. You know, first we ran to figure out where the values were null or no data. We returned 1s and 0s with that to figure out where they were. Now we could go back and actually set those back and kind of revert it to where we were. So, you know, a lot of different ways to protect data using this if you need to. I personally haven't had a chance to. However, maybe you do. Like if you're working with imagery, you could use this to do the same thing. You know, you could, we're just using this with values of 1. Where this could get a little bit more interesting is like with our is null demo right here, instead of test and evaluated for 1, we could start saying where it might be greater than or equal to if we were dealing with elevation. And let's say we wanted to omit certain areas from an area for setback on a building or something like that. We could have ranges set in there greater than or equal to 247.5, and that same elevation layer less than or equal to or greater than or equal to whatever values we want. So this was just just a test for equality for 1 value. So we can really nest this and make these crazy. I love it. It's fun, but baby steps. Baby steps here. This is good stuff. And we're not going to remember all these things, so please keep that in mind. We're introducing a lot of new things to you. And I just want to get into a couple more things and then we'll adjourn. And what I'm going to do tomorrow is I will record another video that sort of helps template what you can do for the assignment. So you basically watch that video and I'll coach you through. But honestly, I think you could probably do the assignment now on your own anyway. But it's all, videos are good. Videos are fun. Okay. Let's come back over here. Thanks for hanging on with me. Trying to get through as much as we can here. Just to make sure And who knows, maybe next week, I don't know, we'll see how it goes. Maybe I'll have a live virtual session where we can go through some of this too. You know, not required or anything, but I'll maybe just, I could record it live for you. If people want to come in, you can do that. I could demo some things out, but again, those are not required for blended periods or anything. Okay. We jump to 322. 322. You know, take a look at this a little bit on your own. It's not, you're not get, no one would ever in their right mind ask you anything on an exam about this. In fact, probably only the basic things, like what are the three things you might find in a VAT? You know, that might be on an exam or something, but I'm not going to ask you anything like this. This just shows you how these, like when you're processing a raster, the compression, the run length compression encoding for how that's sort of packaging up your data. That's what this is really showing here. But give this a little read and let's jump to 436 if we can. 436 here, and want to highlight a few of the various types of analyses that you will be working through in coming weeks. You know, we're not going to be working with set cell. We're not going to be working with, these are just analysis environments, but we are going to work with the mask for our assignment. And I would like to kind of show you a little bit on how we can use a mask as a processing environment. And then that will probably be where we'll call it good in terms of where we're at here tonight. So let's come back over to Pro, and you can remove all of your demos if you want, or whatever we just created there. That's no problem. We can remove those. Cal Topo Grid, maybe we'll leave in there. Let's go ahead and add some data in. I just want to show you the site mask, some of that work, because it pertains to our assignment a little bit, and thought it might be helpful in the next few minutes to go through that before we adjourn. There's a raster out here called a site mask. Let's go ahead and add that into our session. Again, this is under our grid training in our grid intro. So if you navigate down, you'll find that raster layer called the site mask. Let's go ahead and select OK. We'll bring that into our session. All right, let's zoom to layer. I'm going to select right click on my site mask and zoom to layer. And we just have a big blob here. Now, if we turn on our Cal Topo grid, kind of right under that, this is meant to be a processing mask to show you how we can use rasters as sort of clips in a way, but also as a way of controlling our data a little bit more. And so I mentioned earlier, I wanted to just introduce you to what's called a condition statement, or how we could start subsetting data. And we'll try to do a little bit of that here shortly. So what do we have with our site mask? Let's explore our data here for a few more minutes. So if we're checking out our data, we look at our attribute table. We know that, again, do not confuse our ID with our value here, but we know that our entire raster is composed of values of 1. And there are 415,486 cells that contain the value of 1 here. So that's good for us to know. We can also tell our value by looking at our information here in our table of contents. What do you think this is? A continuous raster or an integer/discrete raster? We should already know it, but what were some clues? Let's see, who was that there? Eric, or somebody said something? Or I don't know who it was.
So yeah, I just say continuous, but then I'm looking at the value from top to bottom and they're both one. So that's kind of throwing me off a little.
Okay, what do other people think? Go ahead and unmute there, Megan. Shout it out loud and proud.
I think it's continuous because of the stretch, and when you go into layer properties, it says raster information. Or wait, never mind. The pixel type is not floating, but it's not integer. So I'm taking that as a clue.
Others? We know our cell size is 5. Megan said the pixel type was unassigned character. This is an interesting one, so I wanted to pull it up. Heather, thoughts?
Is it integer and it's just representing one integer?
Heather, nicely stated.
I have
That
nothing
was
to add. to
Nicole.
that.
No, I'm just kidding, Nicole. No, that's, I was just teasing. No, it was good. Thank you, Nicole, for sharing. Heather, what were you going to mention?
I said I have nothing new to add to the group.
Okay. So, yeah, I mean, that's Nicole, basically what was happening there. Like, to me, this is, I don't know how in the heck actually this came to be, but yeah, this color ramp, like Eric was saying, 1 and a 1, it's there. If something is unassigned, always the classic telltale what is that? I can't even time or telltale sign is to check that attribute table. If we can open up that attribute table, you see ID, value, and account, we know that it's an integer. And why is it represented like this? I have no idea, to be honest. It just is. So that's where we're at with that. So coming into this, we know that we have a value of 1. Here's my question to you, and this will be on our exam. I'll give you a question, like a flat out tell you this in some manner. How would you extract out the area underneath this mask to have just the count or the topo, the bathymetry data underneath this mask? That's a question, but we're also going to do this for part of our assignment for next week. Let me show you a couple ways to do that. I'll also do it in the assignment template video I'll put together to help you so you'll see it again. So I want to introduce a couple of ways for us to have a little fun with this. So let's go over into our Nicole, go ahead.
Oh, I thought you were asking us. Go ahead.
Oh no, you take it away, Nicole.
No, I was just gonna ask if we would be clipping it.
We could clip it, possibly. If I were going to ask you to start changing values, it becomes a little bit crazier. Let's step you through some cool things here. All right, let's clear our raster calculator, our geoprocessing area over here by this little erase or clear expression. I'll save that Word document for you all too that had that syntax in it. I'll load that up later. Let's clear that. Now, here are a couple ways we could think about that. Let's say we have our Cal Topo grid and we just double click on Cal Topo grid and we bring that into our raster calculator area. Here's one fun way to do this. If we want to extract out areas underneath that, under environments, click on environments, open that up, and let's scroll down here to where it says raster analysis. You see this thing where it says mask? It's only fitting that it's Halloween right now, like with little masks and stuff out there. This is great. Sort of the same thing. You can only see kind of what's on the outside of a mask sometimes, but we want to capture what's on the inside of this mask. So we're going to select our grid out of here. And where is our site mask? It should be in here. Where did that go? Do you all see site mask? Yeah.
Mine was in there.
So everybody but me. Okay. Well, let me come on.
Yeah,
Here. Let me do
refresh.
a refresh. So when in doubt, there's a little refresh button at the bottom. So basically put the mask in there for your site mask and create a new grid. Call it like site mask demo or something if you want. And I'm going to try to get mine going. That's weird. Well. Maybe I need to remove that.
It's on your list there.
It's here. Let me try it now. Well, site mask. I'm going to type it in. See how that works. No, not really. Well, we'll try it. I don't know what's going on. Okay, well, we'll see how it works. So we want cal topo grid. And now I'm going to set an output name. Again, this is just a name, nothing more complicated or more complicated, just simple. So I'm going to call this one site mask demo. Just name of a grid. So that that gets saved in my directory. All good. I'm just going to check this environments. Okay, well, it says it's on, but we'll see if it really works. What this is going to do is this will create a copy of my cal topo grid with the site mask enforced. So during that copy, it's only going to take out what is underneath that site mask and write it out. So go ahead and click run. I don't know if mine will work or not. I think it did. Now let's turn off our site mask. We don't need that on. And lo and behold, that's one way that we can use a mask to essentially create a copy, drop out what's underneath that. So kind of a cool way. You'll see this in the assignment as a potential option for you, but you'll also see it in 8 weeks. And I'll give you one of these to do. So like little activities like this are funsy little exam things, but we'll do study guides, make sure people are doing okay. But it's another way to sort of clip, but in a different way. I also now, let's go back under parameters, want to introduce you to a new term before we adjourn here for the night. Just want to find it.
Can I ask you a question real quick while you're
You
looking
sure
for that?
can. You bet.
Because I was playing around while you were digging, and I did just cal topo grid minus site mask in the parameters, and it looks like I got the same thing. Would that accomplish the same thing, or is that?
Yeah, if you did say again, Nicole, you went cal topo grid minus site mask?
Yeah.
What you would be yes, but your values might change. Because remember that the site mask had a value of 1. So if you were taking a deduction, what would that look like here? This is what will be happening. If you did, just as an example, if you did cal topo grid, and let's say you had like 1.5 and 2.5, and I'm just making these numbers up, 4.5, and you said minus that of, so this was your cal topo grid, and then you said minus that of the site mask, and you wrote an out grid, whatever that name is, we'll just call it out grid. Don't really know. So if you did a subtraction for that, yeah, I mean, it would in theory only. Did you have your site mask still in force when you did that?
You mean in the environments?
Yep.
For a mask? No, because I did it before you said to do. I was just playing around before you said to do it.
Okay. I mean, anytime you take a subtraction, I mean, it might look the same. I'd have to look at how you had it set up, but yeah, what would happen is that instead of 1.5, you'd be at 0.5 and then 1.5 because you're dealing with the values. Oh, that'd be 3.5. So you'd be really deducting 1 from all the original bathymetry data to your new out grid by doing a subtraction.
And what are you doing when you do the mask? Is that not technically a subtraction?
Not in the case that we just did right here, because what we're doing with that is saying, I'm just taking a copy. I'm just taking a copy, and with a
And
mask,
removing that part?
yeah, it's just letting the other parts go, but it's retaining all the original data in there. So that was when we had the processing mask enforced. But yeah, that was when we just did Cal Topo Grid, set it equal to site mask demo. Said, okay, I'm going to copy Cal Topo Grid. I'm going to call it site mask demo, but the mask was enforced. So creating a copy of it's going to create a copy of all the data. That makes sense. Good question though. Yeah, we could check that out, the subtraction stuff. One last thing, and then we're out of here. Thanks for hanging on. I love this stuff. I know you guys might not, but I really do like this. It's good. So we're going to talk about one last thing to try. You can type this in there. We're going to introduce a new command to you called a condition statement. And this is one of the more powerful analytical tools that we can start to think about and use. And what this is saying, we're going to pretty much type in the same thing in our pro session. Make sure you turn your site mask off, get rid of that in your environment. But I'll type it in here, I'll drop it out under the Word document, and I'll upload again all the syntax for you so that you can practice, as well as what we'll do for the, you're going to see me demo this out again tomorrow for you too. But we're going to introduce something called a condition statement. And we kind of did that with the set null. If you remember that, when we did that set null demo where we said, I want to set null all the data that's tested and evaluated for 1, where it's not, I want to write the L89 data. We're kind of doing the same thing. That's why this might sound a little familiar. But what we're doing is we're saying, wherever the site mask, and I'll just kind of draw that in here again. So site mask we know is all 1. Wherever that's true, we want to write out. Again, we're not necessarily adding these or anything. This is just our site mask. Here's our, well, we had L89. We're dealing with Cal Topo Grid, too. So, but in this example that wait a minute here. Let me make sure. Because L89 is not going to be the same as our site mask. So let me scratch this out here. This is going to be Cal Topo Grid. Sorry about that. All these statements, man, by the end of the night, my head can't focus either. So I'm hanging in there doing what I can do here for you. So what this is saying is, again, these are overlaying here now. I should have put them one under the other, but what this is doing is on the condition where site mask is tested and evaluated for 1, which all these are going to be true on that. Where that is true, we're going to put a true value, which is out of Cal Topo Grid. So Cal Topo Grid might actually have some additional cells out here. And the only cells we're really interested in are, shoot, let me just do this. It'll be easier here for you to see. Here, we'll forget about this one. We'll get that back up. Okay. So this is what's going on here in our statement. So if site mask where it's tested and evaluated for 1, where that's true. So here we have our site mask grid. Now these are the cells that are common right here. Now we see some in the original Cal Topo Grid that's going to fall outside of that mask. Remember that fell outside the mask, that's why we could see it. Here's an example of that. So we're saying in an output now, raster processing will keep areas that in this case, are going to be common to the per cell, like cell by cell, not going to necessarily include anything else beyond that in this type of a process. So this whole function, this condition statement, will give us an out grid, whatever the name of that is. Where this is true, write the values of CalTopo grid. So wherever this is 1, all these are. So we're going to write all these values in again. 1.5, 3.5, 2.5, 4.5. Being that the other parts of CalTopo grid were outside of that, this was either, I suspect, no data. So anything no data times no data, or not times, but if it's no data, it's just going to be no data. So there's not going to be anything here. That's what this is going to do. So let's try it, and then we're out of here. Do the best we can here. So we're going to use our tools over here. We're going to use this con function on the condition where site mask is tested and evaluated. It's a double equals. So we're going to come up here to our tools. Tested and evaluated for 1, not a comma. The parenthesis, get that in there. Where that is true, we're going to write CalTopo grid. Why did that not show up in there? CalTopo grid. And where it's not true, we're going to write a value of 0. I'll highlight this and copy it out for you too. So we're site mask tested evaluated for 1. Where that's true, we're going to write the CalTopo grid values, and where it's not, we're going to write a value of 0. So we won't have any no data. So this might actually be like zeros out here on the end. Let's try that. Did it work for anybody that did try it? Yes. Okay, good. Thanks for working ahead of me here. Beautiful. It's great. Trying to go as quickly as we can, but yet so you can see this so it makes sense. All right, we'll give that a shot. Change this thing here. Con demo. All right, let's run it. Hopefully my syntax is right. Okay, so con demo, there we have it. So that's another way of subsetting. The cool thing about this, if you want to practice between now and then, is that check out where these like 0 or no data values are in our original. And here it says no data. So it's processing everything out as no data outside here. But the fun things are we can set this true value to anything we want. We could call it 1, we could call it 10, we could call it whatever. Practice with that. Just change those parameters out, those true and falses. So thanks for hanging in there. Here's what to expect for next week. Take a look at your agenda. There's a short little assignment in there, get some ideas. Tomorrow, I will template this out for you and maybe a short little 15-minute video that you can watch. I'll kind of coach you through it based on what we did tonight. So stay tuned for next week. I may have a live session optional where we'll go through some of this together if that will help you. But if not, that's okay too. So Eric, Devin, Nicole, our other folks joining us later after the fact here online. Thanks you all for hanging on there. Folks in person, Megan, Heather, Jerry, thank you. Enjoy your evening. We'll see you.
Adios.
We'll see you. What's that,
Thank
Nicole?
you. Take care. Have a good night. Good seeing
Yeah,
you guys.
thank you all. Thanks for hanging in there. I know it was a rough night, lots of stuff there, so thank you.
Take care.
All right, you too. Bye,
Yeah.
everybody.
Bye.